who are not here in attending this session, but he submitted the lecture video. Do you have those video available?
Yes, we have.
Okay. So if the speakers are not here, so then you will play the video, right?
Okay, yeah, we can play.
Okay, good. Thank you. All right, so good morning, everyone. My name is Jibin Pei. So it's my pleasure to introduce our distinguished speakers this morning. And the first speaker is Dr. Bin Xiang from the University of Science and Technology of China. So Dr. Xiang, please go ahead.
Okay, good morning, everyone. And thanks, Dr. Pei, for the introduction. So yeah, my name is Bin Xiang from USTC. So I'm very happy that I can have the chance to share some recent results with you. So today I'm going to talk about van der Waals heterostructure by stacking engineering. Okay. So as we know, the two-dimensional material has attracted intense research intent has attracted intense research interest for the fundamental study and the future device applications because of their unique properties. In general, those 2D materials, they don't have any like dangling bond on the surface of their AB planes. Therefore, those properties provide us a chance to construct or create various heterostructures by stacking different 2D material, just like a Lego blocks. So once we have those kind of like a van der Waals heterostructures, so then what we have is by the interface engineering, we can have the many promising properties such as structure, perturbation, band, renomination, and the spin orbital coupling proximities. Because as we know, as we talked about above, so there is only van der Waals interaction between the layers. Therefore, we can stack different 2D material to construct the different heterostructures. So just recently, Jin Si group from UC Irvine, they have demonstrated a van der Waals heterostructure of graphene layer, a monolayer graphene layer on a ferromagnet YAG heterostructures. And during their studies, they found those long-range ferromagnetic ordering can be induced in the graphene layers through a proximity effect from the YAG, because the YAG is a ferromagnet insulator. So those kind of substrate that can induce the long-range ferromagnetic ordering in the graphene. Then the graphene become a ferromagnetic material. And also the Xiaodong Xu group, they also demonstrate a van der Waals structure. So with the chromium iodine sandwiched by the graphene, they find a GMR effect. Also, people find in those kind of 2D material FGT, this 2D material FGT is a ferromagnetic material. When people put a layer of a topological insulator, Bi2, Te3, bismuth telluride on the top of the FGT layer, then they find the FGT, this FGT Curie temperature, the ferromagnetic Curie temperature, can be increased up to the room temperature, which is very promising. And very recently, also people reported the topological superconductivity in the CRP3 stacked by the NBSE2 heterostructures. So this chromium bromium is a ferromagnetic insulator, which is a 2D materials. And the niobium selenide is a 2D superconductor. When they're stacked together, the interface is a van der Waals interaction. So during this heterostructure, that people find a topological superconductivity, which means in the future, we probably can have the Majorana fermions in the van der Waals heterostructure. So in our work, we are very interested in is exchange coupling effect in the van der Waals heterostructure of anti-ferromagnetic material stacked by the ferromagnetic materials. So the heterostructure is a van der Waals heterostructure because the interface is a van der Waals interaction. So before we go into the experimental data, I would like to tell you what is the exchange coupling. So usually in a pure ferromagnetic system, like let us say the thin film, ferromagnetic material thin film. So we can easily measure the thin film magnetization by the MH curve, which is a very standard characterization. So if the material is a ferromagnetic material, so we can get a very beautiful rectangular shape hysteresis loop. So with the center at the axis of the center, at the magnetic field 0. But when we put the antiferromagnetic layer, like another antiferromagnetic thin film on the top or on the bottom, the pure ferromagnetic material, then when we measure the MH curve, we find that this kind of rectangular shape has a shift. So we call this shift effect exchange coupling. So the shift values people call it exchange bias. So figure B shows the mechanism for the exchange coupling. So when, let us see that when the temperature is higher than the antiferromagnetic near temperature, which means the antiferromagnetic material is a paramagnetic behavior because it's higher than the near temperature, because it is temperature is higher than the near temperature. Then when we measure the system MH curve, so the MH curve shows the pure ferromagnetic MH curve, exactly the same. However, when the temperature decreased below the near temperature, which means the antiferromagnetic material become a spin lines up and become like an antiferromagnetic behavior. Then at the interface, those spins in the ferromagnetic and antiferromagnetic, they will have a coupling. Those kind of coupling give the system an extra energy. Those kind of energy can be the positive, can be the negative, depends on the spins. They are parallel or anti-parallel. That's why you can, when you do the switching of ferromagnetic spins, you will have extra magnetic field or weaker magnetic field. Then you can have the shift either on the left or on the right, depends on the spins lines up at which direction. So this kind of interface exchange coupling, people also call them the AFM pin effect. Okay, so right now the question is, when we talk about the exchange coupling or exchange bias, usually people talk about in the thin film, in the interface growing in a vacuum. But in the van der Waals interface, is there a exchange coupling or not? So in our studies, we choose the 2D material FGT as a ferromagnetic material and the MPS as an antiferromagnetic material. From those kind of data, you can see the MPS is the antiferromagnetic and the FGT is ferromagnetic. So we stack them together. We get this kind of very simple van der Waals heterostructure. To study the interface, we did the cross-section TEM calculation for the interface. From this kind of image, you can clearly see there is a sharp interface between the MPS and the FGT. Okay, we have the device. Then the question is how to characterize the exchange bias in this kind of van der Waals heterostructure. Why we have this kind of question? Because usually when we use the mechanical exfoliation to get the van der Waals materials to construct the heterostructure, so the size is very small, like 20 micrometers. So it's hard for us to use the standard squid equipment to measure the MH curve or the ferromagnetism. So here we think about using the Alomos Hall effect to characterize the exchange coupling. Why the Hall effect can be used to characterize this kind of exchange coupling? Because the Alomos Hall effect is related to the material ferromagnetism. For example, if this material is a ferromagnet, when we flow a current, like an electron current along the axis, so because of the external magnetic field, there will have a voltage drop at the transverse direction, which is ordinary Hall effect. But if the material is a ferromagnetic material, besides this kind of ordinary Hall effect, they also have another extra voltage drop because of the material ferromagnetism. So they have the extra voltage drop. This extra voltage drop we call Alomos Hall effect resistance. Therefore, from this equation, we can see the total Hall effect, they include two parts for the ferromagnet. So first part is the ordinary Hall effect. Second part is the Alomos Hall effect. So from this Alomos Hall effect, you can see this M is material ferromagnetism. Therefore, we can use this kind of Alomos Hall to characterize the material ferromagnetism. So from this figure B, you can see the blue curve is a MH curve, and the black solid line is a extracted AHE. We call it Alomos Hall resistivity. We can see they have the similar shape here, similar shape, right? So those kind of peak, you can ignore them because those are represent the topological Hall effect. That's another story. So right now we have the Alomos Hall effect characterization idea. Then we designed the device using the Hall effect feature. So this is the electrode we labeled. So from 1 to 2 electron, we flow the current. Then we measure transverse voltage. We can get the Rx way. We call Rx way is we call the Hall effect resistance. And we also can measure the longitudinal resistance, such as from the electrode 4 and 6, 3 and 5. This figure B is the real device optic image. From the results, we can see in our van der Waals heterostructure, like FGT, MPS heterostructure, we can clearly see the rectangular shape, which means FGT has a ferromagnetism property. And also we can see the rectangular shape has a slightly shift as the dashed line indicate, labeled by the dashed line. So the more interesting results we observed here is from the RXX, which is the longitudinal resistance. We also call the magnetoresistance. We can see there is an anti-symmetric peak we observe, or we say anti-symmetric spike we observed here, which is very interesting. Why we say it's very interesting? Because usually in the ferromagnetic material, you have the Rx is a symmetric, like a butterfly shape, as we showed in the figure D. But in our van der Waals structure, we observed those kind of anti-symmetric. Even in the thin film, like AFM and FM heterostructure, they didn't observe those kind of anti-symmetric spikes. So to explain this kind of anti-symmetrical resistance, we proposed a mechanism. Due to the time limit, I don't want to go to the details. You can check out our paper. We put it here. So basically, is because in our van der Waals heterostructure, the interface exchange coupling that cause the unsynchronized magnetic switching between the interface and the bulk of the FGT during the magnetization reversal. You can imagine we have a thicker, like a thickness enough, this kind of FGT layer. On the top, they have the MPS. So the interface exchange coupling only affect a few layers of FGT layers. They can pin a few layers, but the rest of the FGT layers, they won't be pinned by the MPS antiferromagnetic material. Therefore, during the switching the spin, you want to switch the spin, like reverse the spin directions. So there is a unsynchronized switching. That's why you can have the different resistance states. So to further prove the proposed the mechanism, we decrease the FGT layer down to the 9 nanometer, but we keep the MPS almost the same thickness. We still find, as the figure C showing here, we still can find a rectangular shape and also exchange bias here. But in the RXX, we cannot observe any anti-symmetric resistance, but symmetric butterflies. Okay, so in conclusion is we observed this kind of exchange coupling in a van der Waals structure, not like a solid interface growing in the back. And we also observed an interesting anti-symmetric longitudinal resistance RXX. So in the end, we would like to thank the collaborators and my students. Our funded is by the Chinese government. Okay, thank you for your attention. Hello.
Professor Pei, you're muted.
Hello.
Okay, so we'll take one question from the chat room. So the question is about what's the difference between anonymous Hall effect and normal Hall effect?
Oh, the ordinary Hall effect or the normal Hall effect, we call the ordinary Hall effect is because the external magnetic, when you apply an external magnetic field that have a Lorentz force, then they will turn the electron to the y direction. Then they will have the voltage drop, like a different, because of electrons accumulate at the one direction, then they will have the voltage drop along this transverse direction. This is the ordinary Hall effect. But for the anomalous Hall effect, because the material itself has the ferromagnetism, this kind of ferromagnetism, the spin moment, they will have a spin moment with the orbiter. They will this kind of spin will have an effect with the orbiter. They call the spin orbiter effect. This kind of spin orbiter effect, they will also can turn the electron on the another direction. This is an extra electron accumulation. Then, which means in the total Hall resistance or total Hall voltage, you will have a, besides the ordinary Hall effect voltage, you will have extra voltage you can measure. That kind of voltage is called alarmed Hall effect.
All right, thank you. Thank you very much, Professor Xiang.
Yeah, thank you for the, thank you, bye-bye.
Yeah, so our next speaker, Dr. Hai Yo Den is a speaker here. So it does not look like our speaker is here right now.
Hi,
so
Professor Xiang. We also don't have his video.
Okay,
He didn't
good.
provide it.
Okay, in this,
Excuse me,
okay, then we
we
yes.
have the video. We have the video. I can play.
Yes, please.
Just wait a minute, please.
My name is Hayo Ping from Cardiff University, UK. So today I'm going to report on the theoretical design of quantum cascade laser that operates in the near infrared region based on van der Waals materials. So the story of quantum cascade laser began with a paper that was written in 1971 by Kazarynov and Suris, half a century ago. They noticed that a superlattice of quantum waves, which is normally represented like this, can display certain negative.
Excuse me, we can only hear the sound, but there is no video.
And that means there's an electromagnetic perimeter in the system, which can be used to amplify electric waves when pass through this material. So the quantum wave normally consists of several discrete levels, right? In the absence of electric field, these levels would be just the same. But when you apply electric field, then they'll be shifted to each other, like in this case, into like a staircase like this. So the idea is to now if you apply electric current, so when electric current going through this medium, in the carriers, the electrons, for example, would transit to a bottom level, and they emit photons. And then, if the electric field is applied in such a way that this bottom level matches the upper level, then this will just roll out to this bottom level again and be transmitted again. So these electrons will be recycled in the downstream stages, and every time
Okay, so I guess we take a short break. We start the next presentation at 8:30 a.m. All right, so welcome back, everybody. Let me introduce our next invited speaker, Dr. Hua Zhou from Argonne National Laboratory. Dr. Zhou, please.
Okay, can I be here?
Yes.
Okay, let me, can you see my screen? Let me go to the full screen. Okay.
Yes, I can see it.
Can you see the full screen?
No, I see the presenter screen.
Oh, presenter screen. Let's see. How can I go to the? How about this right now? Is the full screen or still present?
Presenter screen. There is a switch somewhere you can change.
Okay, let me just see. Okay, let me share again for the desktop. It may be better. Yeah, let me share the desktop. Can you see the desktop?
Yeah.
How about right now? Is still?
No, still presenter screens.
Okay, swap display. How about right now?
Yeah, perfect.
Okay, great. So thanks for that. So yeah, I'm pleasure to present my talk in this interesting conference. Although we're supposed to meet in LA, but because of the COVID, so hopefully next year. Okay, so the first speaker give a very nice coverage about like van der Waals keto structure. So right now my talk is more focused on characterization side and to provide interesting technique or method to give audience, so which we can using that for probing a lot of this interesting keto structure interface, especially showing a lot of emerging quantum phenomena, no matter from van der Waals keto structure or from complex oxide. So yeah, so today my talk is focused on atomic imaging function heterostructure interface by trying measuring the coherent Bragg rod for quantum material. I'm Hua Zhou from Argonne National Laboratory. I'm working on the synchrotron light source called Advanced photon source. So the first speaker talked about the van der Waals keto structure. So I want to like more focus on this complex oxide. Although very last part of my talk, I'm also going to talk about new development toward van der Waals keto structure. So as key showing that for van der Waals keto structure, but also in the complex oxide keto structure, no matter within the keto structure itself or in the interface, there are a lot of very interesting, exciting, fascinating, emerging phenomenon due to this quantum confinement effect, quantum proximity effect, or also new quantum state, no matter from like a strong correlating interaction or topological interaction. So here, just a few examples. People in the last 10 years find out what's happening at the oxide interface. No matter it's 2D electron gas, Hall gas, superconductivity, and also magnetic skyrmion, and also even some like a very colossal ionic conductivity, which is more relevant to the energy application. So yeah, that's today's my more my focus. So for those kind of keto structure and interface, including van der Waals keto structure, there are a lot of very important structure and a chemical aspect about a keto structure itself, about interface itself, which is all waiting for our understanding before we can link the very exciting functionality and performance and atomic level or molecular level information, so we can establish such a correlation. So in order to do that, you really want to learn a lot of very fundamental level, the structure or chemical structure, the keto structure, the interface, and the surface. So here I just give a few quick example, and then what kind of feature we have. So in order to address those kind of like a very fundamental question, we needed some very unique tool probing not just the bulk material, but also only the keto structure itself, or the interface or surface. So in order to do that, we're using a very dedicated, a kind of like an atomic probe using X-ray probe to study this kind of reduced dimension material. So today I'm more focused on this, we call it a surface diffraction method, or a coherent Bragg rod method to address this kind of question. So basically this kind of, a Bragg rod, or we call it truncation rod method, it's pretty simple. It's basically what you learn everything about a bulk crystallographer, a lot of information, a lot of your knowledge of a bulk crystallographer can be easily transfer to this surface, crystallographer. So basically, the crystal truncation rod is one form of a surface, scattering, a surface crystallographer. So rather than focusing on the Bragg peak coming from the bulk material, more focus on something like, if you see my mouse, this kind of very continuous varying intensity when you measure in the reciprocal space, rather than focus on the Bragg peak, we'll more focus on the mid-zone intensity. So those part of the intensity from the scattering is dedicated coming from the surface or interface of your system. So they're very sensitive to surface interface. So rather than just a single crystal, we can go to the keto structure. So we can see, we also see, a lot of very subtle feature due to this kind of keto structure, due to the interface. So if we can reconstruct, get a full atomic structure for this truncation rod, we can learn a lot of information about the surface interface and the complete keto structure. So that's today's we're focused on. And then rather than using a regular model dependent fitting, we try to using some free retrieval method can reconstruct a three-dimensional atomic structure of your whole keto structure, interface, and the surface. So basically, just like you're resolving bulk crystallographer, but we're more focused on surface crystallography. So that's the take-home message. Okay, so I want to give a few very good examples from complex oxide, how we're going to use this surface scattering technique to resolve this oxide keto structure for a lot of emerging quantum phenomena. So the first few examples of that's all coming from the complex oxide. By thinking all the knowledge or method we're using here can easily migrate into any other keto structure interface, including Van der Waals keto structure, 2D material, other a new type of 2D material, topological 2D material. So using the method, we can, for sure, this is a quick summary about we're using this technique. We can really measure a lot of this kind of oxide keto structure for 2D electron gas, whole gas, to study the polar metal, to study interfacial superconductivity, or even like this kind of magnetic topologic insulator interface. So here are the few quick example. One example, for example, I want to show is using this extra surface probe. We can really reconstruct atomic interface for this kind of like emerging 2D electron gas or whole gas. So this is a few monolayer or unicell thin film, less than aluminate, grow on strong zinc titanate substrate, and then you can capping another strong zinc titanium oxide in top layer. You're forming two kind of interface. So the 2D electron gas or 2D whole gas kind of forming at a two interface. And using this X-ray method, we can really fully reconstruct the three-dimensional electron density to learn about this interface. We can see that we can really mapping this kind of like a very sharp, top and the bottom interface. We can get a lot of subtle information about a chemical profile, about a lattice profile. For example, a lattice parameter layer by layer, atomic layer by layer. And now also we can see how sharp interface it is, how important this is sharp interface relevant to this 2D electron gas or 2D whole gas formation. So except to see this kind of like overall shape, we also can provide a very subtle information about atomic rumpling. A very subtle atomic rumpling within the oxide keto structure also can respond for this emergent quantum phenomena. For example, we study another system called a polar metal. So this material is a complex oxide. They're totally metallic, but they also show very strong polarization. So this is something people call a polar metal. So in order to understand this phenomenon, polar metal, we study two kind of systems. One is there's a nailed nickel grow on LAO, but there's along 001 termination. That one doesn't show polar metal. That one just show like a regular MIT transition. So this one really showing that at atomic level we don't see any atomic rumpling. So everything just like a more or less like a bulk structure. So this correlated with also STEM results. And then, but when we go to another termination, it's called 111 termination. Here, the symmetries break. And then they can form in this kind of polar metal behavior. And using this surface atomic method, we can really see the very subtle atomic rumpling between the cation, the niobium cation, and the oxygen atom. So they're rather than in the same plane, but they have this kind of like off-center displacement. So this kind of A side cation displacement can explain where this polarization come from. So this is like atomic structure basis for this oxide polar metal formation. So this is the one that, another example, how does, surface atomic probe can give you atomic, subtle atomic buckling information for the emerging quantum phenomena. So except we can see there's a very high, Z element like a neodymium, we also can see very subtle movement of the oxygen. So within the perovskite, system, one very important building block is the octahedral rotation. So I think this is not just for like an oxide perovskite, but also for right now very hot topic for highlight perovskite. They also have this kind of like octahedral, this kind of building block rotation. So using this SAM, this surface atomic probe, we can really map out this three-dimensional electron density, can give you the idea about how this octahedral rotation evolving within this oxide helium structure. So this is the one example using calcium titanium oxide perovskite grow on different kind of substrate, and then because different substrate, different symmetry, different string state, they can really creating this kind of like a different type of octahedral rotation, a different string, and then also tweaking this octahedral rotation pattern. So using this method, we can really see the very subtle detail about how the octahedral rotating responds as a response to the different string state, a different symmetry of due to the substrate. So, and also this result can fully compare with what you can learn from STM. STM is really from very, very local, very atomic scale. Here, actually, what we learn, although the electron density profile is also atomic scale, but the information basically is a statistic averaging for a lot of unit cell, a lot of domain within your thin film, rather than just a very nanoscale information. And also, this method have an advantage because we can provide a truly three-dimensional atomic structure. Sometimes this information cannot be easily extracted from STM because of this geometry, because of the projection limitation. So that's a big advantage. So far what we're using just based on the Z base, which is a electron density base, reconstruction, electron density based observation. So also combining a big advantage for synchrotron X-ray, we can tweaking the X-ray energy, across some particular elements absorption edge. We also can learn, obtain rather than just a total electron density, but element stress electron density. Here is a good example. So showing the Lanson-Strongson cobalt oxide helium structure on STO, rather than see the total electron density, we also can dedicatedly only showing element specific, the Strongson profile within the system. So this will show us how the Strongson have a non-trivial element profile within the helium structure from the bulk of the film to the top surface of the film. And here really showing very clearly the Strongson is not uniform distributed. They're really showing this kind of segregation behavior, especially near the top surface. They're showing this a Strongson huge segregation and forming rather than just a flat thin film, but also forming some kind of nano island or nanostructure. This is more relevant to energy conversion. So although it's an oxide, a complex oxide, but it's a more relevant to energy application. So this gives example how the element specific atomic probe for surface structure or interface structure of a helium structure, atomic helium structure. So far what I'm showing here just like a lot of ex situ measurement. So rather than showing ex situ behavior, we also can probing what happening for the for your oxide helium structure within operando environmental. For example, we can using ionic liquid, ionic gel to tweaking, like for example, this a very surprising superconductor to insulator transition using ion liquid gating to tweaking this kind of helium structure. But during the meantime, we can also measure what's happening from atomic scale during this kind of gating process, especially because we're using high energy X-ray that can easily penetrating through the electrolyte, can really give us atomic structure information about how the atomic structure evolving within this gating. So for example, here we're using this cuprate high TC superconductor example. And when we are gating this material from superconductor insulator, we are really showing the copper oxygen atomic plan, showing a very subtle atomic run plane as a response of your gating. So this gating really changing atomic, subtle atomic structure arrangement, which is responsible for this superconductivity to insulator transition, because a copper oxygen plan, the cuprate plan, have this kind of very subtle atomic run plan. So because of the time limitation, I want to just last 1 minute, just show very quickly, rather than just see there's a kind of like a phenomenon, see complex oxide structure, we're also extending this a study to a lot of emerging 2D crystal, especially Van der Waals 2D crystal. So a lot of 2D Van der Waals 2D crystal is either their size very small, like mesoscale, or they're putting on very non-trivial surface, like highly curvature surface, and also there's sometimes people can using ultra fast laser to probe this kind of like Van der Waals structure, forming dynamic phenomena. So this same technique can migrate into a lot of the systems. So we can using X-ray focused X-ray beam to micron or nanoscale to study this kind of like Van der Waals structure. For example, like graphene or boron nitride, we can showing how the subtle structure change of the boron nitride or the graphene layer on top of a boron nitride, how does atomic structure subtle change near the interface. And also we can really study how does a 2D material on this kind of like a high curvature surface, for example, moly disulfur putting on some kind of sphere and using sphere to realize so-called band gap engineering, but also we can using this nanoscale or micron scale X-ray beam to probing how the structure will evolve when you're changing the curvature from flat surface to this highly curvature surface, which is showing this kind of lattice expansion. So transient state also we can using like rather than regular X-ray, we can using free electron, X-ray free electron laser to probing how the dynamic change of the heterostructure. For example, here is a tungsten diselenide, how they're responding with the ultra fast laser pump probe, and then see how the dynamic structure, evolution of this kind of heterostructure. So I think I want to really summarize it. And the surface X-ray provide a very unique tool to probing a lot of emerging phenomena structurally, chemically, and electronically for this oxide heterostructure, and also a lot of emerging Van der Waals 2D material. So this is I want to wrap up my talk. So thank you.
Thank you, Dr. Zhou. So there is no question from the chat room, and also we are already passing the time limit, so we will move on.
Okay.
Thank you very much, Dr. Zhou. So the next speaker is Dr. Paulo Arrocio. Dr. Arrocio, can you put up your slides?
Yeah, I'm sure. Okay, do you see it?
Yeah, I see the screen now.
Okay, perfect.
Yeah, perfect. Well, it's my pleasure to introduce Dr. Paulo Arrocio, our invited speaker from University of Milano. Please.
Thank you, Professor, and I want to thank also the organizer to giving me the opportunity to show you some chemical physical parameters crucial for proton NMR relaxation and the work of my group of the last more or less 9-8 years, in particular on iron oxide crucial nanoparticles. So the talk today is focused on the intrinsic characteristic of nanoparticles like composition, size, the shape, the coating and functionalization, and some external parameters like temperature, solution, and external applied magnetic field that are able to influence strongly the NMR relaxometry of magnetic nanomaterials. In particular, today I want to show you some results that regards the application of this kind of material in magnetic resonance imaging. Magnetic nanoparticles are constituted by a magnetic part that is normally done of simple ferrites or ferrites doped with different metallic ions, and of an organic part that is crucial for the biocompatibility of magnetic nanoparticles. So it's extremely important for the application in biomedical field. So which kind of nanoparticles can be synthesized? There are really many examples of nanoparticles, but today I want to focus only on the easiest one, the core shell magnetic nanoparticles. If we look at the nanoscale, the magnetism of this kind of materials change dramatically. In fact, if we are able to obtain, synthesize magnetic nanoparticle of a proper dimension, that depends clearly on the metallic ion that we are using, we obtain this situation where all the electronic spins of our materials are aligned along the same orientation. And so we obtain the giant spin, a giant spin of our nanomaterials. And in the case that the magnetic anisotropy energy is comparable to the thermal energy, we observe the so-called superparamagnetism phenomenon. That means that our nanomaterials behaves like a paramagnet, but with a huge magnetization, like a ferromagnet. So in the case of the easiest magnetic nanoparticles, the core shell one, the magnetism is easy in the sense that we have only one magnetic anisotropy z axis. And so we can imagine that we have only two energetic minima, and that the inversion of the magnetization from the one to the other is made through a current movement of all the spin through an energetic barrier that is governed by the magnetic anisotropy and by the dimension of our nanomaterials. And this movement is described by the nil correlation time. This is true for the non-interacting nanoparticles. In the case of interacting nanoparticle, we can adopt the Vogel-Fulker model where we add an interacting parameter. This picture is true only in the case that we don't yet apply an external magnetic field. As soon as we apply an external magnetic field, the situation changes dramatically, as you can see here. So the energetic levels change completely. So for instance, applying the external magnetic field, we have this situation, but not only. If we manage the temperature, for instance, going down to the temperature, we are able to reopen the loop, the hysteresis loop of our material. And in particular, in the case for the application in biomedical field, magnetic nanoparticles normally are dispersed in solvent. So we have to take into account also the Brownian contribution to the relaxation of the materials. So I hope to have shown you in these few slides that it's important to study both the macroscopic condition and the microscopic parameters of these materials to understand their physical properties. If we try to understand how magnetic nanoparticles can act as T2 negative contrast agents in MRI, we have to see the MRI signal. If we look at the signal, we see immediately that it depends on the local proton density, and so depends on the magnetic susceptibility of the tissue of the body, of our body, and depends on intrinsic nuclear relaxation times of the tissue, T2 and T1, but not only. Because the contrast in the image can also depend on other parameters, like the intensity of the external magnetic field, depends on the type of radio frequency pulse sequence that we use to obtain the image, and can depend on the contrast agents, on the injection of contrast agents in the tissue. And the contrast agents are able to modify the nuclear relaxation time. In particular, for magnetic nanoparticles, the changes of their dipolar local field can induce, through a hyperfine interaction, a change in the relaxation of the local probe, that in the case of MRI, are the protons of the water molecules that pass near the magnetic nanoparticles. So studying the fundamental experimental parameters of NMR, the spectrum, the spin-spin and spin lattice relaxation times T2 and T1, we are able to study the local magnetic field and the spin dynamics of our nanomaterials. Moreover, the efficiency in contrasting imaging for magnetic nanoparticles is expressed through the nuclear relaxivity that represents the increase of nuclear relaxation rate of hydrogen nuclei in presence of the magnetic center. How can study deeply the magnetic relaxation properties of our materials? We need to study the nuclear magnetic resonance dispersion profiles. So we need to study the proton relaxivity in function of the proton Larmor frequency, or if you prefer, in function of the magnetic field applied. And we obtain this kind of profiles. Describing and these profiles, we are able to extract many information regarding our nanomaterials. In particular, for spherical magnetic nanoparticles, non-interacting and with dimension below 20 nanometers, Rock, Muller, and Gillis proposed a well-known model, analytic exact model, and after heuristic approximate expression that are able to describe this kind of profiles. And using this type of models, we are able to obtain many information regarding the distance of minimum approach of the water molecules near the nanoparticles. We can obtain information regarding the magnetic anisotropy of the materials, the nil time, and so on. The theory predicts that these profiles depends on the dimension, the nil time, the magnetization of our nanoparticles, and predicts that at low fields, R1 and R2 are coincident. So, starting from this framework, my group started to work 10 years ago, more or less, and tried to test by experimental point of view many different types of magnetic nanoparticles. And today I talk about core shell results that we obtained in these years. We started with magnetite nanoparticles of different size and different coated. And as you can see, we obtain experimental data that confirms that R1 depends on the magnetic core dimension. But using the model proposed by, the heuristic model proposed by Rock and Muller, we obtain, fitting our experimental data, we obtain also quantitative results regarding the near correlation time, regarding the distance of minimum approach of the water molecule, and regarding the anisotropy of our materials. Passing the years, we tested other type of nanoparticles, and we obtained, for the first time, a complete experimental R2 relaxivity profiles, also at really low fields. So in this case, we are able to test on this type of magnetite doped with nickel and cobalt at different amount, as you can see here, but with the same size dimension of the nanoparticles. We are able to test the model both on R1 and on R2 profile. What we observe is that, as expected, the relaxation properties depend on the magnetic ion, the type of magnetic ion. But using the same fitting parameter obtained for R1, we are not able, as you can see in the figures, we are not able to fit the R2 profiles of these materials. In the same years, we try to test also other type of class of magnetic nanoparticles. In this case, we obtain results on maghemite of different size, but with the same coating. And we observed the same results, that the relaxation depends strongly on magnetic ion core dimension. But again, we fail to fit with the Rock model our R2 data. At the same time, we try to understand the possible effect of the shape and dispersant on the relaxation properties. So we test this effect on maghemite nanoparticles, and we obtain results on spherical or cubic nanoparticles and nanoparticles dispersed in hexane or in water. And what we observed is that shape as an effect, as you can see in this case, the cubic efficiency, the efficiency of the cubic nanoparticles is lower with respect to the spherical one. But for instance, for the solvent, the situation is more complex. As you can see here, passing from hexane to water, in the case of R1, seems that the efficiency goes down strongly, while for R2, seems we obtain best results for spherical nanoparticle dispersed in water. And just the last example that I report to you, we started last year to try to study also the effect of the coating, the eventual effect of the coating. We started with maghemite nanoparticles of these dimensions, coated with different polar electrolytes reported here. And the result, experimental data, say us that probably there is no effect of the coating on the relaxation properties. But it should be said that probably we need to go to a smaller dimension because we think that the effect of the coating is more evident for canted surface spins. And to obtain a quantity, a valuable quantity of canted surface spins with respect to interior spins, we need to go to a smaller dimension with respect to the 8 nanometer that we tested. So just some final comments. We can say that nowadays the ferrites synthesis is well controlled, so we can obtain any type of nanomaterials, magnetic nanoparticles if you want. For sure, we can say that magnetic properties rely on dimension and kind of magnetic ion, but for sure, I can say you that we need to make more and more studies regarding the shape and the coating or surface spins to try to understand if also these two characteristics can affect the nuclear relaxation properties. The fact that we was not able to fit R2 and R1 profile with the same fitting parameters means that theoretical model has missed some mechanism. And so we need to more specific model for this complex multifunctional magnetic nanoparticles. And the last message is that today I talked about the in vitro results, but in principle, seeing the application of this system, we have to talk about in vivo results, but this is a completely another story. Thank you for your attention.
Thank you, Dr. Aroso. We can take one question if there's any.
Yeah.
All right. So without that, so thank you very much,
thank you,
Dr. Aroso. Thank you for
you.
the nice work. Let's move on to the next one. So Dr. Junhui Hu does not look like speaker is here.
Shall we play his video? We have
Yes,
one
please.
video.
Yes. Thank you.
Morning, good afternoon, and good evening. I'm Junhui Hu from the State Key Laboratory of Mechanics and Control of Mechanical Structures, Nanjing University of Aeronautics and Astronautics. The title of my talk is Controlled Concentration and Transportation of Nanoparticles at the Interface between Grain, Substrate, and Droplet. This is outline of my talk, background and purpose of this research, the manipulation method and its functions, working principle analysis, performance, and conclusions. the concentration and the transportation of nanoscale materials. Lots of applications, such as in the fabrication in nano sensors and electrodes, in the high sensitivity biosensing. We may use the magnetic optical microfluidic, dielectrophoretic, and ultrasonic methods to implement the controlled concentration and rotation. However, it has been a big challenge to design a device with dual nano manipulation functions, such as nano concentration and transportation. The purpose of this work is to propose and develop an ultrasonic device capable of concentrating nanoparticles at the interface between a droplet and a plane substrate, and capable of transporting the concentrated nanostructured material at the interface. This is the experimental setup and device we used in our experiment. The experiments were carried out under an optical microscope. This is a device, and this is a substrate. On the substrate, there is a droplet in which there are no samples and the ionized water. Let's look at the device. The device consists of a micro probe, vibration transmission needle, and a piezoelectric component. So they are the main parts of the device. The piezoelectric component excites the whole device to vibrate. Due to the vibration of the microprobe in the droplet, there is an ultrasonic field. With this ultrasonic field, we can calculate the nanosamples in the droplet. In the experiments, we use silicon nanoparticles with a diameter of 500 nanometer. The radius of the microprobe is 10 microns. During the operation, the microprobe vibrates in parallel with the substrate. This probe vibrates in this way. Also, the angle made by the vibration transmission needle and the microprobe is close to 90 degrees, and the distance between the probe and the substrate is about several 10 microns. These photos show a concentration process of the silicon nanoparticles. After 300 seconds sonication, we can get concentration spot with a diameter about 100 microns. The thickness of this is about 20 microns. So the size of this concentration spot is large enough for the fabrication of a nano SN. These photos show the transportation of the concentrated microprobe. I mean, by shifting the device or the microprobe, we can change the location of transported. We can change the location of the concentrated microspot, like this one. Here we have a video and clip. Standard the working principle. We computed the MMP vibration ultrasonic field, the acoustic stream field by an element method. First of all, we use the measured vibration velocities of the MMP to compute the vibration response of the MMP. Then we compute the sound field in the droplet and the driving force of the acoustic streaming. I mean the stress gradient that we can evaluate the acoustic streaming. Computed acoustic streaming at the interface and the PMP are shown by these two figures, respectively. Use the acoustic streaming for as this one shows the acoustic field. That's the below the group. From this figure, from the left figure, we can see that acoustic streaming flow at the interface can from the nanoscale pulse this region to the region. So this one. And with the figure, the right one. From this figure, we can see that acoustic velocity on the substrate under the microprobe's tip, I mean this part. So the nanoscale particles in can stay and fall. This shows the measurement of the concentrated spot versus station time. From this figure, you can see that it takes several minutes to form a stable concentration spot. So from the result, we see that the concentration of suspension basis, this stable diameter, stable origin spot also increases. This is because of there are more nanoscale particles in the droplet with the concentration increases. This figure shows the measured stable diameter velocity of the device. From this figure, we can see that as the vibration velocity increases, stable diameter of the concentration spot increases. This is because the vibration velocity increases, the streaming interface becomes stronger. We also computed the inference, the effect of the device parameters on the flow pattern at the interface. So with these computation results, we can understand, we can know how to choose, how to design the device. Based on the computation, we found that the microprobe's radius R matters. When this radius is too small or too large, the flow at the interface cannot flush the particles to some region. Okay. We also found that the distance between the microprobe and the substrate, when the distance is too small, there is no concentration, and when the distance is too large, there's also no concentration. So the must be in a proper range to get the concentration effect. In our experiments, the range is from 10 microns to 120 microns. Also, we found that the angle made by the VTN and the micron probe can affect the concentration effect. The angle must be around 90 degrees to get strong enough concentration effect. Our computation, we also found that the MMP's length has an effect on the concentration, on the concentration capability. When the MMP's length is proper, the MMP can resonate. So in this case, the concentration effect is quite strong. Conclusions. A facile ultrasonic method for the concentration and the transportation of nanoparticles is proposed. There is no need, in this method, there is no need to set vibration excitation mechanism, the micron channels in the substrate. The concentration process can be implemented at any desired location at the interface, and the the transportation can be implemented through an arbitrarily selected path, the interface. To thank my students for their contributions to this work. Thank you very much.
Okay, so since the speaker is not here, so we'll skip the Q&A session. Let's move on to the next invited presentation by Dr. Ratiba Bazerga. So Dr. Bazerga, can you put up your slides?
Good morning. Can you please use the recorded video?
Excuse me, Professor, do you want to play your video?
So
Can
Dr.
you please-
Bazerga is here.
Yeah, but can you use the recorded video, please?
Okay, okay.
Thank you. Good morning. I introduce myself. I'm Ratiba Benzerga from ITR Lab, University of Rennes from France. The title of my presentation is Carbon Fibers Based Epoxy Foam Composites from Dielectric Characterization to Electromagnetic Absorption Application. This work is collaboration between the ITR and DGA. Here is the outline of my talk. First, I will present the context of this study. Next, I will present the advantage and limits of the commercial absorber and the proposed solution. Then I will present the dielectric properties of our composites, and I will present the result of some achieved prototype. I will finish my presentation by a conclusion. Let me start with the context of this study. As everybody knows, when an electromagnetic wave arrives on material, a part of this wave is reflected at the interface air material, another part is absorbed inside the material, and the last part is transmitted through this material. For an absorber material, we need low reflection and transmission and high absorption of the electromagnetic waves. There are two types of material absorbers: the magnetic absorbers, which are determined by their complex permeability, real and imaginary part, and magnetic losses. The second type is the dielectric absorbers, which are determined by their complex permittivity and dielectric losses. In our work, we deal with this type of absorbers, and we need a lower permittivity and high losses. Shapes and composition of current absorber materials are extremely varied depending on the target application. We can find absorbing plates which can be magnetic or dielectric absorbers depending on the type of the load, loaded polymer foams which are a dielectric absorber, and also metamaterial absorbers with 2D or 3D geometries. Today, absorber materials are used for different applications. We can find the electromagnetic compatibility for various objects or devices. This material are also used for stealth, for the land or for the naval vehicle, and also for the aircraft, even if for this application the geometry is more important than the material itself for the detection of the radar cross-section. Another application of this absorber materials is the anechoic chambers. This is the intended application of our work. What is an anechoic chamber? It is the chambers used for the radiation measurement of devices. The measurement of the devices cannot be performed in a standard environment because the signal emitted by these devices will be perturbed by parasite electromagnetic waves such as Wi-Fi, which constitute an external pollution. For this reason, a Faraday cage is used. This Faraday cage is used in order to prevent electromagnetic waves from entering. But this Faraday cage will create an internal pollution formed by the multi-reflection of the signal emitted by the antennas or from the measured devices. For this reason, that absorbers are placed in this chamber on the wall, the ceiling, and the floor to simulate a free space environment. Now let's go to the commercial absorber and proposed solution. Today, the most used absorber material in anechoic chambers is composed of polyurethane foam loaded with carbon particles and presents a pyramidal shape. This absorber presents different advantages. The first one is its high dielectric losses induced by the carbon particle loads. The second advantage is its porous structure, which gives its lightness and therefore facilitate its installation in anechoic chamber, and also allow permittivity due to the presence of air. The pyramidal shape of these absorbers allows the gradient of permittivity, which induces low reflections, and likewise the height of absorber can be adapted to the desired operating frequency range. And finally, the pyramid paving allows trapping the reflected waves on the pyramid surfaces. On the other hand, this commercial absorber presents some limitations induced by their elaboration process. In fact, these absorbers are produced by the impregnation in carbon-based solution of the unloaded PU foam. This is possible thanks to the open pores of these foams, but this open pores gives a high flexibility to this material, which induces matching errors and limits the use of complex forms for these absorbers. The second limit of this absorber is the loss of the absorbing load, allowing to an inhomogeneous distribution of carbon, as we can see here with the presence of the load on the bottom of the pyramid, but not in the top. This carbon loss induces a premature aging of the absorber and also constitutes a nanometric pollution. The proposed absorber material is made of the association of epoxy foam with long carbon fibers. First, the use of the epoxy foam allows the integration of the load before foaming process, which allows its trapping in the matrix. This technique permits the use of a variety of loads like particles, but also fibers or grids. Secondly, the use of this matrix, which is rigid, allows an accurate and reproducible matching of the shape, but also a matching in other complex forms. From the other side, the use of long carbon fibers, which are non-volatile, provide a high dielectric losses for low load concentrations without damage to human health. The elaboration method of the epoxy composite is very simple. First, the carbon fibers are added and mixed with the viscous epoxy resin. After that, the hardener is added and also mixed. The mixture is put in the mold for the foaming and polymerization steps. Here we have a short movie of this foaming step. Of course, here is accelerate movie. After this, and after a few hours at ambient temperature, the foam is put in the oven at 60 degrees to complete the polymerization of the foam and to fix its mechanical properties. After this, the foam is cut to the dimensions needed for the characterizations. Here, I present the used configuration for the measurement or simulations of absorbers. In order to estimate the absorption performance of our prototype, we use two antennas and the prototype in the same condition that its application. It means with a metallic plate placed on the back of this prototype. Antennas are placed on the front of the prototype in order to send waves and also to recover the reflected waves. Here, these reflected waves are the results of the reflected wave at the interface of the absorbers, air and material, and also non-absorbed waves which are reflected by the metallic plates. To have an idea of the value of reflection coefficient, we can see this example. When this reflection coefficient is higher than minus 10 dB, which means more than 10% of the incident waves are reflected, we have a bad absorbers. This value must be lower than minus 10 dB, and of course here we are looking for the lowest possible value of this reflection coefficient. So now I will present the dielectric properties of our composites. Here I will present the permittivity and dielectric losses of simple maze with a different carbon fiber length. These measurements were done with a coaxial probe. First, these measurements show very low dielectric properties and also only small variation of these properties as a function of carbon fiber content for sample made with 100 micrometer fiber length. With fiber length of 1 millimeter, we observe a larger variation of dielectric properties. Here, these properties increase with fiber content. Same observation can be done for the fiber length of 3 millimeter, and we can note here that we have higher dielectric losses for a lower weight percentage of carbon fiber. In order to see this effect, here I compare two samples. The first made with 3% of carbon fiber of 1 millimeter length, and the second made with only 0.5% of carbon fiber of 3 millimeter length. We can note here that we have approximately the same dielectric losses with load content 6 times lower for material with 3 millimeter fiber length. And for the samples, we have a lower permittivity for the sample made with 0.5% of carbon fiber of 3 millimeter length. So the sample presents the best dielectric properties with lower load rate. For this reason, this composition has been chosen to elaborate absorber prototypes for this work. So now I will present the achieved prototypes and their characterization. The chosen geometry for the first achieved prototype is that of the commercial absorber EPM-12 from Siepel. The dimensions of this pyramidal absorber are shown here. The reflection coefficient of the two prototypes, absorber epoxy-based absorber and commercial one, are measured in the anechoic chamber for different incidence angles. Here is the reflection coefficient of the commercial absorber as a function of frequency and of the incidence angle of the waves. And here is the scale of the reflection coefficient between -15 on red and -50 in dark blue. We can note here for our result for the epoxy prototype that we obtain a dark blue coloration compared to the commercial one, which indicate a low reflection coefficient, so a better absorption in all the steady frequency range and incidence angles. For a better observation, I will present now the cross-section of the reflection coefficient obtained from the previous measurement at the normal incidence of the electromagnetic waves. On this figure, we can observe the improvement of the reflection coefficient with the epoxy prototype here in blue curve, and here a mean value of the optimization of is about 10 dB is obtained on the static frequency range with a maximum optimization of 25 dB. Here is the cross-section of the previous result for oblique incidence of 30 degrees. We always observe the improvement of the reflection coefficient with the epoxy prototype. A mean gain here is about 6 dB. We can observe the same optimization and improvement with other different angles. Now, the same composite was used to achieve another prototype with a complex geometry. Here is the picture of this proposed prototype. This first confirms the possibility of complex geometry with this rigid epoxy foam, which is our first target goal. The measurement of this prototype was also done in anechoic chamber and compared to commercial absorber. Here are presented the measured reflection coefficient for the normal and oblique incidence of the waves. We can observe that an excellent absorption performance is obtained in the interstudied frequency band for our epoxy prototype. Better improvement is observed here with this geometry up to 30 dB compared to the commercial absorber. So let's conclude. So I can say that we proposed a new composition for absorber materials based on epoxy foam loaded with long carbon fibers. The achieved pyramidal prototype based on epoxy foam loaded with low weight percentage of only 0.5% of 3 mm length of carbon fibers shows a better absorption performance than commercial absorber. We proposed also a new shape of absorber which confirmed the possibility of matching of complex geometry with this composite, and the achieved prototype shows an improvement of the absorption performance up to 30 dB for the normal and oblique incidence in all the studied frequency range. So to finish, I would like to thank Jérôme Sol for his technical support and all these different organizations for their financial supports, and thank you for your attention.
All right, thank you, Dr. Prozega. Are you willing to take questions?
Any question?
I don't see any in the audience. I have one question. So your absorber is looks like it appears white. So the commercial product is black. Is there any advantage of having it to be sort of light colored?
Mm-hmm. In fact, this is due to the concentration of the load. The commercial one is the carbon load in the commercial one is higher than the concentration in our prototypes, and also it is due to the type of the load. The carbon black give this black color more easily than the carbon fiber, of course.
Yes. Good. Thank you very much, Dr. Prozega. So,
thank you.
Yes, we'll move on to the next presentation. Dr. Jim Nam does not look like Dr. Nam is here.
Okay, I will. Maybe we can
have
share.
The video, right?
Yeah. Yes, we have the video.
Please.
Hello, I'm Jin Nam from University of California. First of all, I'd like to thank the organizers for inviting me to present some of our recent findings in our transformative piezoelectric enhancement of electrodes from PVDF therapy nanofibers and their bio-applications. As you probably know, piezoelectric material is a class of materials that can convert mechanical energy to electrical energy, or vice versa. There is an increasing interest in utilizing these piezoelectric materials for bio-applications, such as electrical stimulator, on-demand drug delivery platform, and bioenergy scavenger system. Traditional inorganic materials, piezoelectric materials, provide the best opportunity because of their high piezoelectric performance, but the drawback of such material is that their mechanical brittleness, which causes foreign body reaction in the body when implanted. In comparison, organic materials like polyvinylidene fluoride or PVDF provides the mechanical compliance, which is suitable for bio applications, but its inferior piezoelectric properties limit their applications. So there have been research to improve the piezoelectric properties of organic piezoelectric materials, especially PVDF, focusing on transforming the non-piezoelectric alpha phase, shown it here, to piezoelectric active beta phase or gamma phase. One of the approaches is the addition of a phase stabilizer. One example is trifluoroethylene, which will stabilize the beta phase formation at room temperature. Another approach is using mechanical stretching and electrical pooling to align these polymer chains to form beta phase to further improve piezoelectric properties. In this context, the electrospinning is very useful because during the process, the polymer is intrinsically subjected to mechanical stretching during this the electrospinning process, as well as electrical pooling by the applied electrical wires, which improves the formation of a beta phase as well as the alignment of a piezoelectric domain to one direction. So this electrospinning process improves the piezoelectric coefficient of PVDF TRFE from about 20 picometer per volt under the mechanical stretching and electrical pooling to about 30 picometer per volt. However, this improved value is still not up to those you can find from inorganic piezoelectric materials. So in this study, to further improve the piezoelectric properties of PVDF TRFE material, we hypothesized that the dimensional reduction of individual fibers in these electrospun fibers would further improve polymer chain alignment, which will in turn improve the piezoelectric properties. To test our hypothesis, we utilized design of experiments where we controlled the fiber diameter by utilizing variation in solution properties that will affect electrospinning process, including viscosity, electrical conductivity, and surface tension by means of regulating the polymer solution concentration, the addition of organic salt, as well as surfactant. So by going through several of these DOE experiments, we were able to downsizing the fiber diameter to 30 nanometer. We next examined the crystallinity of these electrospun nanofibers with having different fiber diameters and using our XRD experiment. And we found that by decreasing the average fiber diameter, there was a linear increase in degree of crystallinity, almost to 80% when we spun 30 nanometer fiber diameter, and which further improved to about 83% when the sample was heat treated at 90 Celsius degree. In order to examine the electroactive phase content, we utilized FTIR on nanofibers having different fiber diameters, similar to XRD data, where we examined the crystallinity. By decreasing fiber diameter, the electroactive phase content linearly increased almost up to 90% in the smallest fiber diameter, which further improved to almost 95% when heat treated it at 90 Celsius degree. We checked the piezoelectric coefficient, D33 value of these fibers with respect to different fiber diameter, and surprisingly, we found that D33 substantially or exponentially increased, especially below 100 nanometer. And this substantial increase in D33 could not be fully explained by the improvement in crystallinity as well as the piezoelectric phase content increase we examined using XRD and FTIR. To look into the mechanisms behind this substantial increase in piezoelectric properties or piezoelectric coefficient, we utilized piezo force response microscopy to determine the domain dipole alignment in these fibers. So it started with the 19 nanometer electrospun fibers. When we downsized the fiber diameter to 30 nanometer, we saw improvement in the piezoelectric dipole alignment as shown in this histogram. In addition, when they were subjected to thermal treatment, we also saw improvement in dipole alignment. And when we apply both of these dimensional reduction and thermal treatment, there is a substantial improvement in the phase domain alignment as determined by this histogram. Another possible explanation why we saw that substantial increase in piezoelectric properties when the sample, the fiber was downsized below almost to 30 nanometer is that maybe it is because of the materialization of flexoelectricity. So it has been known that electrospinning intrinsically produces this core shaft structure in electrospun fiber. These shows the cross-sectional images of individual electrospun fibers in 30 nanometer and 90 nanometer. There's a formation of a sheet because of faster evaporation of solvent during electrospinning process, and the composition percentage of this sheet material as compared to the core is greater in 30 nanometer as compared to this larger fiber, which causes substantial increase in strain gradient within the structure. They may have realized the flexoelectricity in addition to piezoelectricity in these fibers. So by using these improved piezoelectric properties of PVDF TRFP nanofibers, we tested our material for several different bio applications. One include the energy harvesting. So we placed the electrospun fibers underneath this armband, and when you flex your muscle, which will subject the fibers to compressive forces, you can light up these LED light bulb. And depending on the performance of your fibers, you can turn on 3 lights at the same time without capacitor, or you can turn on almost 10 LED lights using 30 nanometer fiber size. Another application we are using these piezoelectric nanofibers is for nerve tissue engineering, where we culture neural stem cells on these electrospun PVDF therapy nanofiber substrate, placed into these casings, apply hydrostatic pressure to this scaffold, which will convert this mechanical stimulation into electrical stimulation to the cells cultured on top of it. As shown here, there's a voltage induction upon stimulated by the hydrostatic pressure applied to this scaffold. So what we found is that when you culture the cells on the same scaffold and apply electrical stimulation by using typical traditional electrode and power source, where we found that most of the cells differentiated toward neurons, as identified this red stain. Same thing here, most of the cells differentiated toward the neuron. When the cells were subjected to mechanoelectrical stimulation by using this piezoelectric material, there was a simultaneous differentiation of these stem cells toward both neurons stained by the red color, as well as astrocyte identified by the green staining. Similarly, we saw simultaneous spontaneous differentiation toward both neurons as well as oligodendrocyte. Also, when we culture the cells aesthetically, where we saw cells differentiate both type, but there was not much of interaction between different cell type as shown here. As compared to that, when the cells were subjected to mechanoelectrical stimulation, it not only enhanced the simultaneous differentiation toward the different phenotypes of the cells, but also it enhanced interaction between those different types of cells, as identified by these myelin sheet formation surrounding axons. So these improved cell interaction resulted in greater magnitude of action potential generation, longer duration of action potential, as well as a faster response velocity of this engineered tissue under the mechanoelectrical stimulation. Another application we are using our PVDF therapy nanofiber scaffold is for the on-demand drug delivery application, where we utilize the intrinsically negative zeta potential of PVDF which would attract the cationic drugs. Once the scaffold or the substrate is activated by mechanical perturbation, that changes the surface polarity of these PVDF-TRFE nanofibers, pushing the cationic drugs away from the surface, releasing those to environment. So in our preliminary study using our rat model, where we implanted model drug loaded PVDF-TRFE nanofiber membrane subcutaneously and then applied the mechanical stimulation using shockwave system, we were able to control drug release on demand. In conclusion, as we demonstrated, we achieved a transformative enhancement in the piezoelectric properties of PVDF-TRFE nanofibers by using electrospinning. The dimensional reduction and thermal treatment not only increased the overall electroactive phase content, but also enhanced the dipole alignment, piezoelectric dipole alignment, leading to substantially improved piezoelectricity. This enhanced piezoelectric performance allowed us to use these PVDF-TRFE nanofibers for various bio applications. I have to give all the credits to my graduate students who worked on these projects, including Gerardo, Yui, and Karen. I also want to thank and acknowledge my funding sources shown it here. If you have any questions, please shoot me an email to email address shown it here. Thank you very much for your attention.
All right, so let's move on. I'm pleased to introduce our next speaker, Dr. Masataka Hagashiwaki from the National Institute of Information and Communication Technology, Japan. Dr. Higashiwaki, the floor is yours.
All right, thank you. And yeah, could you play my video as my presentation?
Sure, we will share.
Hello, everyone. I'm Masataka Higashiwaki from NICT Japan. So today I would like to give a talk on our high-frequency beta-gamma oxide field effect transistors for application to harsh environment electronics. This shows outline of my talk today. As an introduction, first I'd like to introduce briefly and material properties and the features of beta-gamma oxide. And then I'll move on to the main topic, highly scaled gallium oxide MOSFETs, device structure, DC, RF device characteristics, and also the delay time analysis. And then I conclude my talk towards the end. So, introduction. So you may know them very well, but first I'd like to introduce basic material properties of gallium oxide. So gallium oxide has several types of polymorphs from alpha to copper. So among them, beta is the most stable phase corresponding to monoclinic beta carrier structure as shown here. So all the other polymorphs are metastable phases. So gallium oxide has two strong points and two drawbacks. First of all, gallium oxide has an extremely large band-gap energy. So in case of the beta, it's about 4.5 eV, and most popular and metastable phase, alpha gallium oxide, it has a band-gap energy of 5.3 electron volt. And also we can control the electron density and also the n-type conductivity by using the normal donor doping technology. So in your case, we've already succeeded in controlling electron density in a wide range from 10 to the 15 to the 10 to the 19th by using silicon or tin as a donor dopant. And also, as I mentioned, and there are two severe drawbacks. First, there has been no report on p-type doping and also the effective core conductivity. So we have a deep acceptor, therefore we can make the PN junction to have a large barrier, but it's impossible to have the effective hole conduction. So this is basically due to the basic material properties of gallium oxide and also the general oxide materials. And also the gallium oxide has a poor thermal conductivity. It's also the typical and material property for oxide semiconductors. So the thermal conductivity of gallium oxide is less than 1/10 of those of silicon carbide and gallium nitride. Of course, and this is a very severe issue for the heat dissipation of the gallium oxide power devices. What I'm showing here is comparisons of material properties between major semiconductors and beta gallium oxide. So as I talked, beta gallium oxide has a large band-gap energy of 4.5 eV. And if you see the direct constant, it's a 10 to 12. So this is almost the same as those of other semiconductors. And breakdown electric field. So this is one of the most appealing points for gallium oxide. So it's a recent over 7 megavolt per centimeter. So this value is larger than those of silicon carbide gallium nitride. And room temperature electron mobility, it's expected to be around 200. So this is due to the relatively small energy branch of optical phonon. And of course, the optical phonon scattering dominates room temperature electron mobility, even in case of the gallium oxide. And the saturation electron velocity, it's okay. It's also same as those of silicon and the gallium arsenide, and slightly smaller than those of silicon carbide and gallium nitride. And the thermal conductivity, so as you see, it's terrible. It's a recent and less than 1/10 of those of silicon carbide, gallium nitride. And if we calculate the barrier film rate, and as you know, so this is the most popular figure of merit to see how suitable the material is for power device applications. It's very good. It's larger than those of silicon carbide, gallium nitride. But today I'm going to talk about the high-frequency gallium oxide transistors. Therefore, the Johnson's figure of merit is much more important. So if we calculate the Johnson's FOM, as you see, it's almost the same as that of gallium nitride. But in case of the high-frequency applications, heat dissipation is much more important than the power devices. Therefore, this and the low thermal conductivity affects the severe degradation of the device performance in case of the gallium oxide FETs. Therefore, I think the gallium oxide and the high-frequency FETs doesn't have the benefit expected from the Johnson's figure of merit. So there is another and important feature for gallium oxide. I mean, beta gallium oxide wafers can be produced from bulk single crystals synthesized by melt growth methods. So we can use any type of the melt growth methods, such as Chokolowski, floating zone, Bridgman, and EFG. So here, and I'd like to introduce the technique of EFG. So it's very simple. We put the gallium oxide powder source into the crucible and heat it and melt it. And then if we put the dye with a narrow slit as shown here, and then the molten gallium oxide comes out of the slit due to the capillary effect. And if we put the seed crystal and pull it, we can get a plate-shaped bulk crystals. So there are these kind of the merits for the EFG. And numerical crystal technology, this is the main vendor of the gallium oxide wafers right now. They have already demonstrated the production of the 6-inch diameter gallium oxide wafer, and also if we see the crystal quality of the bulk wafers, it's already good, at least and enough good for the development of the vertical and lateral FETs and Schottky barrier diodes. From the viewpoint of its extremely large band of energy, gallium oxide is of course promising for high power and high voltage applications. But the large band of energy can offer the other possibilities. One of them is harsh environment electronics. So harsh environment includes this kind of the applications and the atmosphere, space, underground resource survey, nuclear plant. Basically, the environment, silicon and the other existing compound semiconductor devices cannot be operated for a long term. So this large bunch of energy can offer the long-term stability of gallium oxide devices, even at high temperature and under the strong radiation. Therefore, I'd like to emphasize and also propose that gallium oxide FET should be useful not only for the power switching applications, but also the harsh environment electronics. So based on this kind of idea, we started the development of gallium oxide RF transistors. So here, and I'd like to introduce the fabrication and device characteristics of our first generation high-frequency gallium oxide transistors. So let me move on to the main topic of this talk, highly scaled gallium oxide MOSFETs. So we used plasma-assisted MB machine for the preparation of the epitaxial wafers. So these are the gross conditions. Epitaxial structure was very simple. On top of iron doped semi-insulating gallium oxide 010 substrate, we grew a UID gallium oxide layer with a thickness of 200 nanometer. That's it. And then we processed the FETs using the epitaxial wafers. So this is a schematic cross-section of the device structure we fabricated by using the MB-grown epi wafers. So, into the UID gallium oxide layer, we performed 2x silicon impression doping to make channel and also the ohmic contact regions. And after the 2-time ion implantation, we performed the activation annealing at 925 degrees C. And then we made the source and drain and electrode by using the titanium-based metal stack. And then we deposited in the 20 nanometer thick aluminum oxide layer by using ALD. Finally, we fabricated T-gates with gate lengths of 50 to 1000 nanometers. So except for the T-gates, this device structure was fabricated by using our typical and process conditions. So this shows a typical DC IDVD characteristics of the gallium oxide MOSFET we fabricated. So this device had a gate length of 200 nanometers. So as you see, we got a beautiful IDVD curves. So drain current was perfectly controlled by the VG bias sink, and also we got a good pinch-off characteristics too. And maximum drain current density was 300 millimeter at a gate bias of +4 volt. This shows transfer characteristics of the same MOSFETs with a gate length of 200 nanometers. So this measurement was done at a drain bias of 10 volt. So as you see, we got a peak GM of 70 millisiemens per millimeter. So this is reasonably good for the device structure. And also we got a good controllability of the drain current by the gate bias sink as shown here. What I'm showing here is small signal characteristics of the same device with a gate length of 200 nanometers. So this measurement was done at a VD of 10 volt and a VG of -20 volt. So as you see, FT was estimated by the extrapolation of current gain, and it was estimated to be 9 gigahertz. On the other hand, Fmax was determined by the frequency that both MAG and UG become 0 dB, and it was 27 gigahertz. So I'd like to mention that this Fmax value is the record for the gallium oxide FETs. These are gate length dependencies of FT and Fmax. As you see, FT monotonically increases with decreasing gate length down to 150 nanometers and saturates at about 10 gigahertz for the further reduction of the gate length. On the other hand, in case of the Fmax also increases with decreasing gate length and peaks at about 200 nanometers and starts to decrease for the further reduction of the gate length. So these two features are saturation and also the reduction. These two features are definitely due to the significant short channel effect. Next, we performed a simple delay time analysis based on the gate length dependence of FT. So total delay time can be derived from the inverse of the FT, and the total delay time is composed of 3 parameters: intrinsic delay and drain delay and channel charging delay. And this intrinsic transit delay corresponds to a delay in carrier transport across a region under a gate. And the drain and the channel charging delays, both of them can be considered as a constant irrespective of gate length. What I'm showing here is the gate length dependence on total delay time. So as you see, total delay time decreases monotonically with decreasing gate length down to 200 nanometers and saturates at 16 to 18 picoseconds. So this saturation is definitely due to the short channel effect. And also that we extract the effective electron density from this slope under the presumption that the tau drain and tau charge are constant irrespective of gate length. So from the slope, we can derive the effective electron velocity, and it's estimated to be about 2 times 10 to the 6. So conclusion. In conclusion, we fabricated some micron gallium arsenide MOSFETs for high-frequency applications. The fabricated MOSFETs demonstrated decent DC characteristics and excellent RF small signal characteristics. Especially the Fmax was a new record for gallium arsenide FETs. However, we also confirmed significant short channel effect for the gate length of less than 200 nanometers. We need to solve the issue to further increase FT and Fmax. We also performed a simple delay time analysis to extract the effective electron velocity, and it was estimated to be about 2 times 10 to the 6 centimeter per sec. So this value is reasonable for the theoretically predicted saturation electron velocity of 1 to 1.5 times 10 to the 7 centimeter per sec. So combined with expected high tolerance against high temperature and radiation stresses, we can consider that gallium arsenide MOSFETs are promising for harsh environment electronics applications. Thank you very much for your kind attention.
Thank you. Are there questions? All right, so if not, let's thank Dr. Higashiwa. A big thank you for your nice talk and nice work. So let's move on to the last invited presentation this morning for this session. Dr. Matteo Tornizza. Are you going to present live or?
If possible, since my connection is not very good, I'm not confident it works. If you have the recording, it's better. Otherwise, I'm here.
Yes, we have your video. We can share it.
Well, thank you.
Thank you.
Hello, my name is Matteo Tornizza, and today I'm going to show you how, using one single metal oxide nanowire, we were able to use it as a gas sensor and assess the freshness of meat and fish products. In the past, groups of human experts were used to assess the quality, the freshness of a food product. Recently, also some scientific instrumentation is added to try to make it more objective. The problem is that, unfortunately, both these ways share the same problem. They are expensive in terms of money, but even more in terms of time. And you cannot waste time while you are assessing freshness that degrades very quickly in time. Therefore, since we need a tool that is different, a sensor, a detector that can do this work quickly, rapidly, I'm going to show you our approach, our solution to this problem. I will start showing the material we used, metal oxide nanowires, then their performance as ammonia detector, in terms of response intensity, speed to respond and recover from the ammonia, and then the limit of detection. Why ammonia? Because ammonia is a component of the so-called total volatile basic nitrogen. That is a group of volatiles used as a, let's say, marker of the meat and fish degradation, because it is produced by the microorganisms that are responsible of the degradation of meat and fish. In the last part, indeed, we will see some measurements of real fish and meat samples compared with their total viable count measurement. That is the standard reference technique for such measurement. Nanowires are obviously wires that are in the scale of the nano, so it means they are 1,000 times thinner than a human hair. You can see here a human hair with the background made of nanowires. In our case, we grow a forest of nanowires with the diameters around 50 nanometers. We pick the ones we want. Here you can see the fringe of the crystal lattice, showing that they are monocrystals. That is important for their conduction properties. And in the last very important picture, you see the actual gas sensor. The sensor itself is the nanowire, because the two metal electrodes here are used only to connect the nanosensor to the macroscopic world with the electronics that acquires the signal, but the sensor itself is this. And how does it work? Basically, the surrounding atmosphere, for example, in this case, the ammonia molecules, they arrive on the surface of the nanowire, and there they react with the surface. They can withdraw or release electrons. In our case, ammonia releases electrons. Therefore, with more electrons, there will be more current and a lower resistance. So measuring the resistance, we can measure, let's say, the concentration of ammonia in our case. Indeed, here we can see that in air, the nanowire has a certain resistance value. When we inject 10 parts per million of ammonia, the resistance goes down to another value. And this ratio, the ratio between these two values, is the response of the sensor to 10 parts per million of ammonia. We can see that this behavior that replicates here works also at higher working temperature. But at higher working temperature, you can here qualitatively see that the response and the recovery are quicker. We can see that the response or response intensity increases with working temperature, and it increases also with the gas concentration, obviously. Another important parameter, well, two are response time and recovery time. And you can see here that they, in the worst conditions, they are 25 seconds and 45 seconds, and then they decrease with increasing gas concentration, and they decrease very much, going down to really few seconds when we increase the working temperature, really down to 2 seconds and 5 seconds, more or less. Another important parameter is the limit of detection. That is the lowest concentration that the sensor can detect. This is very important because without a very low limit of detection, you cannot detect the beginning of the degradation. In our case, you can see that at the lowest working temperature, our limit of detection is 180 parts per billion. And at the highest working temperature, it goes down to 30 parts per billion. Coming to real samples measurement, in this case, mackerel fish samples stored at room temperature, we can see here and read the black curve on the left, that is the response of our gas sensor, and the blue curve on the right, that is the total viable count, the microbial count on the samples, on the same samples. We can see that the two lines overlap quite well with the two curves, and the degradation at the beginning is quite slow, and then it starts to increase its speed, and it reaches the threshold. A value of 7 on the logarithmic scale of total viable count is considered the threshold beyond which the food is not consumable anymore. This threshold is reached after more or less 18 hours. When we instead measure samples stored in a refrigerator at 4 Celsius degrees, we see that again the two curves are overlapping quite well. In this case, the degradation is very slow for 18 hours, then it starts to increase its speed, but the threshold is reached after a much longer time, 40 hours more or less. If we use the fact that the curves overlap quite well to use it as a calibration, so we use the previous data as a calibration, this line, we see that some random samples, some random measurements, both of samples stored at room temperature and in the refrigerator, follow quite well this line. This means that the response of our sensor can be considered a good estimate, a reliable estimate of the total viable count, an indirect measurement, but a good, reliable measurement of the total viable count, with some benefits. It is non-invasive, so we don't need to cut out a small piece like with total viable count or gas spectrometry or other techniques. So we just need to put the sensor close to the fish and sniff it. It is quick because we have seen that it's a matter of seconds, let's say maximum 1 minute instead of hours like other techniques. It is simple because everybody can do it. It's just a matter of putting the sensor there and read what the sensor says. You don't need trained personnel, and it is much cheaper than the techniques that are nowadays used. The problem is this works, and it works well for mackerel fish. Would it work for tuna fish, for example? Well, for sure it would work somehow, because the total volatile basic nitrogen is the marker for any kind of meat or fish degradation. But since the calibration most probably wouldn't be the same, we wouldn't know what we are measuring. Okay, more is more degraded, higher response, let's say, is more degraded, but we don't really know. We would need another calibration, but then how can the sensor know which calibration to use? For this reason, we decided to apply another approach that we recently developed, that is basically mimicking the electronic noses. Traditional electronic noses combine the responses coming from different sensors made of different materials. Here we do the same using the same sensor, so the same material, working at different working temperatures. Combining these responses, we can do the same and use it as an electronic nose. What happens is this. This is a principal component analysis, and you can see here that at time 0, when the samples are fresh, we are here, and then coming down to 64, 80, 70, 80 hours, more or less, we can follow somehow the degradation of the samples, and we can even distinguish a bit the pork on the left, this from cyan to blue, and the marble trout samples here. So it seems that the two groups of points are separated. This means that probably we are able to distinguish the different types of food. Indeed, if we use a support vector machine classifier, we use first one classifier that whose task is to distinguish the two foods. And we can see that on 42 samples, it classifies correctly 40 of them. That is more than 95%, so it's a good classification. Then the 21 samples that are considered pork are given to another classifier, in this case, in one case pork, and for the other samples to a different classifier. In the case of pork, we can see that we use this second classifier to assess the state of freshness. And we can see that 20 of the 21 samples are perfectly classified. One is not, and this unfortunately is a bad error. Why bad error? I put the background green, yellow, and red to mean the importance of the error. Indeed, if our error is as a green background, it means that the sample is actually fresh and it is assessed as fresh, or it is degraded and it is assessed as degraded. So they are, let's say, errors without repercussion. In the yellow area, the sample is fresh, but it is assessed as degraded. So this kind of error leads to food waste. In the worst area, the red one, the sample is degraded, but it is assessed as fresh. So this would lead to food poisoning. This is the worst type of error. And we have this error that is the worst one. We must also say that probably it's not all fault of this classifier, because this sample is exactly this one. It is the sample that actually is degraded trout, but the first classifier said it is pork. So it made a first mistake. So probably the second classifier is a bit confused by this first misclassification. Anyway, only one sample is misclassified. This means, again, more than 95% of correct classification. In the case of marble trout samples, there are more errors. There are 3 errors, but we see that 2 of the errors are errors without repercussions, because these are 2 samples that are degraded and they are assessed as degraded, even a bit more degraded. So the only real error that we should take care is this one. So also in this case, we have, let's say, one real error, one important error. That means that basically, overall, the sensor system can distinguish the 2 food products in more than 95% of the cases and assess correctly their freshness, again, in more than 95% of the cases. In summary, using only one nanowire, so with a very tiny sensor, and measuring their resistance, we are able, using one dynamic resistance, to assess the total viable count, to measure and directly estimate the total viable count of the sample, with some important benefits. The sensor is small, simple, cheap, and very quick. If we combine more than one response, we are able to distinguish different foods and then assess their freshness after we distinguish them. I would like to thank you for listening, for watching my presentation. If you have any questions, I will be glad to answer them. Thank you.
Thank you, Dr. Toneza. So we can take one question, if there is any. Okay, so let's give, this is the final talk of the session. So let's give all the speakers this morning a big applause. All right, thank you all for your attention. So this wraps up the session. Goodbye.
Thank you, Professor Pei. Let's meet at 10:12 later.
All right.
Welcome, Dr. Tim, in the second session of today's conference. Okay, so now you are the chair for the second session, so you can proceed. Thank you.
Yes, thank you. All right, and I think it's already time to get started. Taking over directly from the first session. Taking over here. Luckily, we don't have to change rooms and climb upstairs, so there are benefits with being online on Zoom, and let's make use of that. So welcome to this session. We have 8 excellent presentations for the next 2 hours. So let's try to stick to the schedule so that everyone who wants to join later on can come in at the time which is in the program. So the first speaker should be Juan Carlos Otero. I cannot find the name here online. Am I wrong? Is anyone else presenting the first one live? Otherwise, we will play the video. Right, then I need to ask the local support. Should I play the video or are you going to play it?
Okay, we can play the video.
Thank you. So our first presentation comes from the University of Malaga in Spain.
From the University of Malaga, Spain. I'd like to thank the organizers for giving me the opportunity to talk about the electron transfer processes between molecules and metal cluster or electrodes. The talk is mainly focused on the complex effect of the electron potential in the overall electronic structure of metal molecule hybrids. The energy requirements for electron transfer is summarized in this very popular scheme showing the relative energy of the continuous level of the metal with respect to the energies of the HOMO and LUMO orbitals of the molecule, of the adsorbate. For instance, in the forward metal to molecule charge transfer, an electron of the Fermi level of the metal is transferred to the vacant LUMO orbital of the molecule. If the electron potential is shifted minus 1 volts, the Fermi level rises plus 1 electron volts, and the energy of the charge transfer, metal to molecule charge transfer process is reduced the same quantity, minus 1 electron volt. In the reverse process, an electron of the HOMO of the molecule is transferred to the Fermi level of the metal, and the energy of the molecule to metal charge transfer increases 1 electron volts when the electron potential is shifted minus 1 volt. In these cases, electron transfer requires photon excitation, for instance. This sample scheme is very used in electrochemistry or molecular electronics and implies a direct conversion of the applied electron potential in the energy of the electron transfer process. There is no energy gain because both quantities are equivalent, but this scheme is a very rough approach to the chemical structure, the softer electronic structure of charged interfaces. Surface enhanced Raman scattering is a very powerful technique to get insight into the overall electronic structure of these metal molecule interfaces. The main characteristic of cells is the enormous enhancement of the Raman signal of molecule bonded to silver or gold nanoclusters. This enhancement is a nanoplasmonic effect mainly located in the gaps between two closer nanoparticles. In normal Raman, the ground electronic state of the molecule and a virtual state are involved, but in some cases, Raman becomes resonant and the intensity is further enhanced. Resonant Raman occurs when the energy of the laser excitation, matches the energy of a stationary state of the system. The resonant states can be located in the molecule, for instance, the first excited singlet, in a specific state of the metal. The metal have a lot of electronic transitions, or in new metal molecule charge transfer states. The energy of the CT states are very dependent on the electron potential. Therefore, to discussing resonant Raman process, the energy of the laser excitation must be compared with the energy of this excited state, and so it is necessary to know the entire electronic building of the metal molecule hybrid and the effect of applied potentials in the ground and excited electronic states. A lot of papers dealing with cells or molecular electronics have been published reporting theoretical calculation where the system has been modeled by means of a single or many molecules bonded to large or very large metal clusters. These more or less realistic systems have no manageable, and it is very difficult to include the effect of the potential in the calculations. The applied potential modifies the surface excess of charge of the electrode, and we have simulated the change of the density of charge of the surface through a single molecule like pyridine bonded to the terminal atoms of linear silver clusters with different density of charge. This effective charge is defined by dividing the 0, minus or plus 1 electron, the charge of the overall cluster, by the length, the number of silver atoms. In this series of complexes, the density of charge ranges between minus to plus 0.33 electrons. And now we calculated the effect of the potentials on the electronic structures of the surface complexes. These figures show the calculated dependence of the first excited singlet of pyridine, the S1 state, and several series of forward metal-to-molecule charge transfer states on the density of charge of the clusters. DFT or multi-configurational calculations give the same linear dependence of the energy of the S1 and CD states on Q effective. The CT resonant conditions is fulfilled when the energy of the used laser, the green line for instance, crosses the line of a particular CT state. In this case, the relative surge intensities will reflect the features of this resonant process. Several experiments using different techniques point to a huge effectiveness of the electropotential in turning the energies of the CT process. This energy gain, these experimental values, are very dependent on the particular molecule and the experimental conditions, but large values are obtained in many cases. For instance, the group of Tian have studied the surge of protonated adenine recorded on rhodium and palladium electrodes with 3 different excitation laser lines and have found very large energy gains. This means that one applied volt shifts from 3 to 4 electron volt the energy of the CT states. In order to understand the origin of the gain, we have calculated the dependence of the CT states or rhodium complexes bonded to different nitrogen position of the molecule. All of these complexes bonded to nitrogen 1, 3, or 4 show a similar behavior with a large dependence on the density of charge. However, the complex bonded through the amino group, this red line, is much less sensitive. The slope S quantifies the sensitivity of the particular CT state on the charge transfer on the metal, and the y-intercept quantifies in turn the stability of the molecular anion formed in the transient excited state. The transfer electron is much more stable in the case of protonated adenine and the case bonded 2, the hydrogenium is an intermediate case. We have selected the case of adenine hydrogenium for correlating or calculated results to the experimental SERS excitation profiles reported by Jiang. In this figure, the crossing point between the energy of the 3 laser used and the energy of the city state is correlated to the maxima of the corresponding maxima of the SERS excitation profiles. This procedure allows to correlate the applied electron potential to the effective charge, the density of charge of the metal clusters. This correlation is made through the slope C. C is an electrical capacitance of the metal which quantifies the capability of the metal in converting the applied electron potential in surface charge. Therefore, the electron potentials cannot be directly correlated to the energy of the city process, because the energy gains is the product of the slopes S and C. The metal capacitance is mainly dependent on the nature and the local morphology of the metal, and the slope S is very sensitive to the nature of the molecule, the nature of the metal, the geometry of absorption, the selected city state, and many other experimental conditions. A surprising result is obtained in the case of ionic adsorbates. Theoretical calculations of the structure of isonicotinate and ion bonded to linear silver cluster predict the existence of two different surface complexes. The bottom lines in this figure show the effect of the density of charge of the silver in the stability of the metal molecule complex in the ground electronic state. At positive density of charge, the complex is very stable due to the strong attractive interaction between the negative charge of the molecule and the positive charge of the metal. The bond energy of this chemisorbate complex is not dependent on the applied potential. Conversely, repulsion dominates at negative potentials. This physisorbate complex is much less stable and the energy is very sensitive to the applied potential. Therefore, there are two different complexes of different nature. Concerning the city states, at negative potentials, the system have forward metal to molecule city states, which are very depending on the negative metal charge. These forward city states show large slopes as in the previous case of neutral pyridine or adenine. However, reverse molecule to metal electron transfer dominates at positive potentials. In this last case, the complex is so strong that the electron potential is unable to tune the energy of these states. Therefore, the discussed energy gain is not universal, given that the same system can show different directions of transfer, forward and reverse, and large or even zero energy gain values depending on the range of considered potentials. Obviously, these dual and opposite behaviors of the metal molecule complexes is more evident in charged molecules, but can go unnoticed in neutral adsorbates. In order to confirm the existence of physisorbate and chemisorbate complexes, we have revisited the paper by Billman and Otto about the effect of the electron potential on the size wave numbers of the CN stretching vibration of cyanide solutions using sulfate as electrolyte. The figure shows the surge frequencies of CN recorded at different electron potentials, and three different regions can be seen. The frequencies remains almost constant in region A, but shows a significant dependence at the electron potential more negative than the potential of zero charge of the silver electron in region B. But a sudden jump is observed in the frequencies more positive than minus 0.2 volts. This region C has been assigned to bidentate cyanide complexes bonding to both the metal surface and to silver cations, given that it disappears when the electrolyte contains chloride instead of sulfate. These silver cations are produced at positive electrode potentials. The two regions A and B correspond to perpendicular cyanide bonded to the electrode through the carbon atom on a top coordination. We have calculated the CN wave numbers of the series of top C complexes, and a very good correlation with the experimental results is found. A flat dependence is predicted at positive charge in good agreement with the size wave number recorded in region A. But the calculated frequencies show a sharp dependence on Q effective and negative values, given that it corresponds to the very polarizable Fischer-Solberg complex of region B. Summarizing, metal molecule interfaces are complex systems where the electron potential plays a key and non-trivial role. A single molecule can show a complex behavior depending on the sign of the charge of the electron. The applied potential is able to modulate the properties of these hybrid systems and can select two different electronic structures with control over properties in the ground and excited state states. This conclusion offers new unexpected possibilities of metal molecule interfaces, which can be useful to better understand many basic processes in electrochemistry, heterogeneous absorption or catalysis, or for improving the devices used in energy conversion or in molecular electronics. Thank you very much for your kind attention.
Okay, let's thank Dr. Otero for this presentation. But you should be aware this was a pre-recorded video, so if you have questions, please contact Dr. Otero by email. You can find his contact details in the conference program. But we are happy that our next speaker is present. It's Dr. Das from the University of Maryland Eastern Shore in the US, and he will present a presentation titled Experimental Observation and Theoretical Modeling of Light-Activated Resistance Switching in Single Zinc Oxide Nanowire. We're looking forward to the presentation.
Yeah, just 1 minute. Let me find my file. Okay, so this is not giving me the share screen option. So all windows, just 1 minute. I have too many windows open. Okay, fantastic. Can you hear me all right?
Yes, perfect.
Okay, great. So, good afternoon from Maryland, and I know different participants are from different time zones, so it could be good morning for you, for someone good evening. So let's start without delaying any further. So today my talk is on experimental observation and theoretical modeling of light-activated resistance switching in single zinc oxide nanowire. And this work started with when we created some ethanol and zinc oxide thin film, and surprisingly, when light was shining, visible light was shining on that thin film, we observed a massive resistance change in that zinc oxide thin film, nanowire thin film, and then we found that even in under visible light illumination, there exists two stable ohmic state. one in the dark and one in the other one in the illuminated state. Those are two stable states. I will come into that in a few seconds. And there was a significant delay in transition between these two saturated states. One is dark saturation, one is illuminated saturation. And visible light acted as a non-invasive tuning parameter for this bistable switching, so bistable resistance switching, which is surprising because zinc oxide's band gap does not permit visible lights to create this much change. So we hypothesized that it's the ethanol which was used in the preparation of those thin films might have an effect. So we tried to go deeper into that, and we wanted to see whether it's a thin film effect or it's coming from the single zinc oxide nanowires. So that's why we started working on single zinc oxide nanowire, and we wanted to see whether the similar type of resistance switching happens in single zinc oxide nanowire or not. So this is the first setup for that. We studied zinc oxide thin film. We took a glass slide, and then we created a thin film of zinc oxide ethanol mixture using Doctor's blade method, and then we connected two wires around it, two electrodes, and we measured we did the IV analysis, IV curve, and see whether there is any resistance switching and memory skip behavior and all sort of things. In the middle, you see there are like some plasma etching thing, and at that time we didn't have a plasma chamber, so we created our own plasma using a microwave oven. So that's a different story. That's a separate paper. We further investigated that. You can look for microwave plasma and my last name Das, and this was featured by MIT Technology Review also. That's a cool thing, a cool way to create plasma. But that was a different story. It's called the necessity is the mother of invention. So we had to create that because we didn't have a plasma chamber in our lab at that time. Anyway, so let's come back to the original story. So the first figure on the top left, it shows the IV characterization of that thin film in dark region, dark saturation. And you can see that this is a straight line. It shows the ohmic resistance type. IV is proportional to each other. When there is no light, it's in dark for the thin film. There is another IV characteristic, which is still ohmic. And you see there is the resistance when it is in dark, it's 18 mega ohm, and when it is in light, it's 210 kilo ohm. So there is a big jump in resistance. And if we plot the time versus the current curve here, when the voltage was fixed at 20 volt, you see the moment let me turn on the laser pointer. The moment the light is turned on here, the current started increasing, meaning that the resistance is decreasing after a while. If you wait for long enough, it will come to a saturated value, and then as the light is turned on, resistance starts to decrease and follow this line. So that was the effect, and this is the blown up picture of that. And so we wanted to see whether we observe the same phenomena for a single zinc oxide nanowire or not. So we created a nanowire bridge between two gold coated electrodes. The nanowire film, so this was, the gap is around 2 micron, and we created, and this white line you can see here, that is a single zinc oxide nanowire. And the way we created this bridge is called the electrophoresis method, dielectrophoresis. Here in between these two electrodes, you create a very high frequency AC voltage. So it's like 20 megahertz frequency. We used 2 volt to 3 volt potential difference between these two electrodes. And you put a drop of zinc oxide solution in ethanol and water. And then if you observe it from the top using a microscope, just normal table microscope, you will see that these zinc oxide nanowire starts to oscillate to align itself along the electric field, and then eventually it gets stuck between these two electrodes. So it's a repeatable and robust way to create the bridges. Obviously, in some cases, you will see a lot of bridges, a lot more nanowire. So you have to create very dilute solution of zinc oxide in ethanol to get these bridges. So this dielectrophoresis method we use to create the bridges. After we created that bridge, then we brought that nanowire bridge under the solar illuminator, solar simulator, and then there is an oscilloscope. We changed we changed the voltage and the current. We changed the frequency, and then there is a light beam here, and in between the light beam there is a light chopper. It's just like a fan blade. It rotates and it chops the light. So at some time it's illuminated, for some time it's in the dark region, depending on the speed of the light chopper. So this is a standard setup, and then we checked whether this nanowire bridge is showing any sign of resistance switching or not, and it did. It showed that the nanowire, the voltage, when it is current limited, the voltage goes back and forth. The voltage increases and decreases as the light is illuminated, and when it is in the dark. So light turned on and light turned off. You can see the voltage is increasing and decreasing. When it is current limited, that means the current is constant, voltage is changing. So the obvious conclusion is that the resistance is changing. So that's the resistance changing of a single zinc oxide nanowire. And here we saw that there is a difference of time scale, decay time scale, and growth time scale also. The growth time scale is in the millisecond order. The decay time scale is in the microseconds, a few hundred microseconds order. And if you remember the time scale in the zinc oxide thin film, there is a huge difference, order of magnitude difference. That was thousands of seconds in zinc oxide, bulk zinc oxide thin film. That was the time scale for resistance switching. Here we can bring it down to millisecond order, and we believe we can even bring it to further down to microsecond and sub-microsecond order by changing the length of the nanowire also. So what is going on, and can we create a mathematical modeling of to understand this whole phenomenon? So that was our goal, to start modeling, and we hypothesized that because of the ethanol presence of ethanol in zinc oxide, there is some oxygen molecule absorption on the surface of the nanowires, and as the oxygen molecules get absorbed on the surface of the nanowire, it traps some of the free electrons from the nanowire. So this is, as the electrons get trapped at the surface, there is the mobility of the electrons diminished, and that contributes to the lower resistance of the, higher resistance of the nanowire. And as the light increases, as the light shines on those nanowires, these oxygen molecules get untrapped, dissolved from the surface, and then the trapped electrons, they are free to go back to the conduction band, and it starts to flow, and you can observe lower resistance or higher currents. So that was our hypothesis. And we created the mathematical modeling. We solved the differential equations, and we got the structure of the current like this. And when we compared the theoretical modeling results with the experimental data, they matched quite well. Not absolutely, but you can see there is slight difference, but we could match the experimental data with our theoretical modeling and to prove our point. So most likely this is the adsorption of oxygen molecule on the surface of the zinc oxide nanowires that is creating this phenomena. And this we applied that model for the bulk thin film also, where the time scale is much larger, and it worked quite well, not perfectly, because I can imagine that there are much more impurities. So there is a lot of deviation from the theoretical modeling. But if I go back to the single zinc oxide nanowire, the theoretical modeling and experimental data matches much better. So this is sort of and we did some comparison between zinc oxide nanowire and nanoparticle. All of them show similar trend, and I don't want to go into the details of the mathematical modeling. You can check that from our paper, and I'd like to thank everyone for paying your attention, and thank you for giving me the opportunity to present my work, and thanks to our funding agencies, NSF and Department of Education, for funding this research. Thank you very much.
Thank you very much, Kutas, for this very exciting and interesting presentation. I have to admit, I liked also the part with the microwave, but let's stay more here to the science of the zinc
I would
oxide.
encourage all of you to just Google microwave plasma and my last name Das. You'll get it.
There's a question in the chat that is, if you blocked UV light during your experiments?
Yes, we did. We did block UV light during our experiment. That's why it is surprising. And this results for the thin film was published in Scientific Reports, and it became one of the top 100 most downloaded papers. So please check Scientific Reports for more details.
Then I have a few questions. Do you have an idea of what exactly is the effect that the sunlight is sufficient to dissolve the oxygen atoms? Is that something which is well known from zinc oxide surfaces? Or?
That's a very good question. I don't know. So my next aim was to actually to do this experiment in a vacuum chamber and see if I get rid of the oxygen, all the oxygen content from the chamber, and if I do the same experiment, whether they show the resistance switching or not. Probably that will answer that question.
Yes, it's very good point.
Yeah.
Did you try to vary the wavelength, if it is,
yes,
or the intensity of the light, so to change some parameters of the light?
Yes, we did, and it shows. Let me. So this is not this one. Yeah. So we used colored filters and UV light filters and changing the wavelength also. There is difference of switching, but it works there. And then we did some hysteresis, low hysteresis analysis also. So it shows some pinched hysteresis, which is a signature of memoristic behavior.
Okay. Yes. Do we have some idea to use this effect for making photosensors or something similar?
Yeah, photosensors and memoristic chips like the neuromorphic circuits. If we can bring it down to much faster time scale, then that could be a way to build some neuromorphic chips, computer chips, which can work in a non-invasive way. You can create different levels of memory. If you look at like 0 and 1, one is high resistive, one is low resistive states, then you can create different levels of zeros and ones depending on the light intensity and light frequency. So that can create a dynamic memory range.
Thank you very much again. Very interesting work.
Thank
Now
you.
I have to ask again if we have the speaker for the next presentation, Dr. Kwon or anyone, another presenter from Postec Korea to present the next talk. If so, please turn on your camera or raise a hand. If not, then Dr. Jingjuan, can you please again play the video for the next presentation?
Now, for brain studies, cerebral spinal fluid is very important. Also, you need to study ion concentrations in blood. Once you are able to use actors, PQR chips, non-invasive diagnosis may become possible in the future. Reason is this. For spectral details, look at this FTIR spectrum with different cases of bond lengths. That FTIR uses interference length changes for the spectrum. For actors case, use multi-mode PQR chips with angle resolved coherent changes. Now those studies can be done to ears, eyes, nose, throat, anywhere possible. And also the signal can be improved with correlation function studies, especially time correlation functions for blood flow mapping, hemodynamics, for pressure variations. Conclusions. We have seen non-invasive diagnosis with multi-mode actors, PQR chips. There is some need for improvement, bandpass filter technique and the correlation function technique. Thank you.
Okay, well, we thank the speaker who was unfortunately not present for this interesting but a bit short presentation, which brings us to the point that we are ahead of schedule, which is also something one should avoid, but we have the next speaker here, Dr. Jacques Noudem. So I would ask you, do you want to start already now and have some 5 minutes extra, or do you want to wait until we have the scheduled time?
Oh, I can start now. It's wrong.
Okay, perfect. Yes, then let me introduce our next speaker from Normandy University, Dr. Jacques Noudem. Sorry if I pronounce wrongly your name, with the presentation overview of spark plasma sintering of functional ceramics.
Okay, I don't know if you can share my. Can you share my screen?
We can see it.
Just sorry. Yeah. Let me just put the full screen. Okay. Anyway, do you have the full screen or not yet?
No, not yet.
Oh, sorry for that.
Yes, now it's excellent.
Okay, I will also remove the video because I am afraid that I can have with the Wi-Fi, I can have some problem. Okay, well, first I would like to, first of all, to thank the organizer to give us opportunity to present our work to this meeting. And also just to thank all of you who's online today, and good morning or afternoon to some of you and all of you online. My today's talk will be about an overview of spark plasma sintering of functional material. I am Jacques Noudem from Caen University, but let me just acknowledge all my co-workers, Mrs. Zing,
Dr. David Souriau and Professor Pierre Beinstein and Dr. Sophie Rivoira from different labs here in France. Oh, I don't know if this, oh, well, okay, it's okay. Okay, the structure of my talk is as follows. I will just answer two questions. What is the spar plasma sintering, where I will go through the principle and some mechanism, and what can the spar plasma process do, where I will just share three examples. The first one will be about the superconducting magnesium diboride cryomagnet. The centering of recycling neodymium iron bar permanent magnet. And the third example will be about the layer structure bismuth-based superconducting material before to conclude. Well, let's just start with the first part, where after the brief history, I will just answer this first question before to develop the principle and the basic mechanism. Well, regarding the history, the spar plasma technique was patented in 1960s by the Japanese researcher. But in 1990s is the introduction of the large units of this technique in the lab. And here are, like you can clearly observe here, the different providers around the world for such kind of this technique. Well, in this slide, you have here the different main companies with the machine where we use in our lab. This is the FCT German company one. Regarding the question, what is really the spar plasma sintering? Let's just note that this is the non-conventional sintering technique, combining the high current and quite high mechanical pressure to directly through the powder to densify, because what we are looking here is to consolidate this powder and investigate the properties behind. This shows some main advantages as the fast heating rate, up to 500 degrees C per minute, the lower sintering time. This can be decreased up to 200 degrees C compared to the conventional sintering or hot pressing sintering, and also the shorter processing time, less than an hour. But all this lead to the obtain the quite high sintering kinetic. Well, another advantages of SPS, spar plasma sintering, is the significant sample densification, where the grain, you can point out the grain growth control, and also the texturing. That means the grain alignment when you have the sample is randomly oriented like this. But for that, you should start with some layer structure materials, can be able by controlling the temperature, the apply pressure or the dwell time to induce the grain alignment, like you can clearly observe here with the C-axis, the crystallographic C-axis parallel to the main, the average C-axis parallel to the applied pressure. Well, by using this technique, basically this SPS allowed to prepare the large family of materials as ceramics, polymers, materials, metals, and also some composite materials. Now let's move to the principle of spar plasma. This is quite similar as a hot press system techniques, where the hydraulic part, like you can see here, allowed to control the applied pressure. But the main difference is the heating system. Here, the current flow directly through the powder where you really want to densify. But we should point out two different stages. The first one is if the powder here inside the mold, the chamber, is the conducting powder, the current will flow directly, or partially if you have the semi-conducting materials. But if the powder here is the insulating powder, the current will flow through the dia. Basically, it's the graphite mold, and this will be hit by indirect heating. And all this is located into this vacuum chamber where you can also control use some inert gas as argon, hydrogen, or also the nitrogen. But we should just point out, like if the powder, like I'm saying, it's a conducting powder, the current will the high critical current density, like you can see here after simulation. This clearly shows that you can obtain some high current density directly through the current, the main part of the current flow directly through the powder. But in case of the ceramic powder as the aluminum oxide, this will flow, the maximum current density is through the mole, like you can clearly observe in this slide, in this picture, sorry. Then this slide just show the centering mechanism. That means the conventional centering versus the SPS centering one. What can you just learn here is in the beginning, you have the initial state where you can clearly observe the neck formation, followed by the expansion of the neck and the plastic deformation. But at the end, you can clearly observe the SPS centering or the conventional centering. You can clearly observe the grand boundary formation at the end of these two. This is clearly attributed to the Joule effect between the grand boundary, like you can see in this part. Well, let me move to the second question. What can we do with the spar plasma centering? Where I'm going to share this three examples where we treated in this work. And I will start with the densification of magnesium diboride, a superconducting magnet. And this MgB2 magnesium diboride is the well-known material since 1953. But the superconducting was discovered in 2001 with the critical temperature around 39 Kelvin. This is an hexagonal structure and also shows some advantages as the strong harness, the lighted materials. But when to prepare this material, we all usually start with some small particle, like you can observe here, the starting powder. But after sintering, by using basically in the literature, most of the people is related to the using conventional sintering technique to prepare this material, but the sample is quite less dense. You can clearly observe here, the density is around 60%. And this is why we will use the SPS, to use SPS to densify these materials. And the main goal of the study is to optimize the densification of this material by using a spar plasma to obtain some compact cryomagnet for some application between 20 to 25 Kelvin. While here we have the as process materials, the different shape, and the sample is also quite dense by using SPS, like up to 98%. This slide shows the temperature dependence of the magnetic moment of basically of the sample prepared, the magnesium diboride prepared by SPS, where the critical temperature is around 39 K, what we are looking for of these materials. But from the cubic samples cut from the pellets prepared by SPS, we record this hysteretic curve at 20 K. And by using the Bing model, he was able to deduce one of the main parameters, the critical current density of the materials. And this curve shows this magnetic dependence of the JC of the sample prepared at a different temperature. What can you learn here is at the higher JC, 250 kiloamps per square centimeter was obtained for the sample prepared at 950 degrees C, but then decrease when we increase the centering temperature. Can clearly observe here. And one explanation here is we form at high temperature the MgB4 phases, and this MgB4 phase increase when you increase the processing temperature. This can be one of the reasons why the JC decrease here at cell field. Well, finally, one of the functional properties show that we can trap the high field, because here you have two pellets prepared by SPS with the Hall sensor between. And when you stack two pellets like this, you can you was able to record the disco where the trap field is around 4 Tesla on this two pellets between two samples. But on top of the single samples at 20K, we record roughly 3 Tesla. But what you can observe here, when we increase the temperature, this was decreased because at 25K, this decreased from 4 to roughly 2 Tesla. But the main thing here is you should be careful about the speed, the magnetic speed applied, because when you increase, we observe some flux jump, like you can clearly observe here, this Dutch curve show that this is one of the critical points. You should really control the speed less than 0.01 Tesla per minute. But the result we obtained here is comparable with some reported data. Okay, now let me just move to the next part of my talk regarding now the neodymium iron bore permanent magnet. This is one of our ongoing projects between our lab, the institutional lab, and also a Valeo company. But the main goal of this work is to investigate the neodymium iron bore powder obtained from the U-band mine deposit. And the main question is, for that, we have some suitable growth of rare air demand, and also due to the increase of human deposit. And for this work is let's just say the permanent magnet, the NLAF permanent magnet was produced by, let's just say, was from Valeo, and by using hydrogen decrepitation, our colleague from Grenoble, they prepare the powder in our lab. We consolidate all this by using spar plasma sintering and microwave heating. And let's just move to the result of this. We start first with the starting material. This is the commercial powder here named Aishi. This is commercially available. And this is the recycled powder where after hydrogen decrepitation, the size of the powder is around 30 micron here. And all this was consolidated by using SPS process. And here we record the shrinkage, the speed means also shrinkage of the boat curve, and where we was able to observe is the maximum shrinkage is around 450 and 425K for the both samples, the recycling, the reference sample and the recycling samples, but the both was quite high, dense, up to 98%. Well, then we perform the magnetic properties of these materials, where you can clearly, we record the MS, the saturated magnetization, the remnant magnetization, and also the coercitive field of these two samples. And like you can clearly observe some differences between the coercitive regarding the conventional powder and also in the recycling powder, like you can clearly observe here. It all was recorded in this table, but one of the parameters, the figure of merit, was recorded here for the both samples, where you can clearly observe some differences between the both samples. When then we compare at the end, we perform the flux mapping on the both samples and compare with the commercial magnet, like you can clearly observe here. Regarding the Aishi samples, we obtain 0.2 Tesla, on top of these samples, and 0.18 Tesla on top of the recycling materials, and 0.35 Tesla on top of the commercial powder. The interesting thing here is the reference samples compared to the recycling powder seem to be quite closer after processing. Let me just move to the last part of this talk regarding the texturing, the SPS spar plasma texturing material using to prepare the superconducting bismuth layer material. Basically, when you prepare this material, it's also quite less dense, like the MgB2, only 60%. But here we use the spar plasma sintering and spar plasma texturing, SPS and SPT. We can clearly observe here, in this case, the powder is directly introduced into the mold. In that case, we start with the pellets, the pre-sintered pellet, and after, during processing, this was deformed in order to induce such kind of orientation between grain, like you can clearly observe here. In the both cases, the sample is quite aligned. Then this slide show again the magnetic properties or measurements on this material performed perpendicular and parallel to the applied magnetic field, where it was able to deduce an anisotropy here. This can be correlated to the microstructure where you obtain. Okay, let me just come to the conclusion to say in the fast hitting SPS allowed to prepare the dense bulk MgB2 cryomagnet, where the track field was quite close to 4 Tesla at 20 K. This was one of the goals of this study. And the recycling permanent magnet show that you can obtain also the magnetic field up to 0.2 Tesla on top of the bulk sample. It is not quite close to the, let's just say, the similar result between the recycling and the reference powder. And by using spar plasma sintering, it was able to induce the grain alignment between superconducting layer structure. Okay, thank you for your attention, and back to you for discussion.
Thank you very much, Dr. Nudem, for this interesting presentation. I think we have time for 1 or 2 questions, so please use the chat or turn on your camera and unmute your microphone if you want to ask something.
Yeah, I can.
Maybe in the meantime, I can, I don't see any questions, so maybe I can ask something. Sorry if I missed that, but can you please point out again for me, what is the special issue of the spark plasma sintering compared to conventional sintering?
Let's just say that one of the main issue of this technique is the sample densification compared to the conventional sintering, where usually the samples show you obtain some low dense materials. Yeah, that is really the main issue. And also, with respect to the conventional sintering, is the fast heating technique, because in a few hours you can prepare the materials compared to few days for the conventional sintering. I can also just say is the energy saving behind all this.
Yes, thank you. Okay, I mean, we saw from the results that you have these impressive results with the high kinetics, as you mentioned exactly. Well, if there are no further questions, then let's thank Dr. Nudem once more, and let us continue to our next presentation, which comes from the National Institute of Advanced Industrial Science and Technology in Japan. And again, I have to ask if we have Dr. Shen with us or one of the co-authors who wants to present. If not, I ask for her to play the video of the next presentation, so that we can go ahead here.
Hi, Professor, can we play their video?
Yes.
Hello, everyone. It is my great honor to give an invited talk at this conference. My name is Guohai Chen. I'm a senior researcher at the CNT Application Research Center, AIST Japan. My talk is entitled Neural Probes and Through-Silicon Via Interposers, Utilizing High Aspect Ratio Carbon Nanotube Arrays. Please feel free to contact me through my email. What are the neural probes and interposer? The neural probe is an electrode used for recording or stimulation of neuron activities. It can be used to heal some movement disorder like Parkinson's diseases. Here is an example called Utah array, implanted inside the brain. There are some potential issues. First, like mechanical mismatch between tissue and probe material, which can cause tissue damage. Also, there are other critical structural requirements, like high density, high aspect ratio, and uniform spatial resolution. Interposer is a critical component in microelectronic packaging for high-density 3D packaging. It's used to bridge between stacked components from fine-pitch input-output contacts to the coarse-pitch package and the substrate. A through-silicon via interposer is the most common type using silicon as substrate and copper as feeding material for high electrical conductivity pathway. Two important features for interposer: high electrical conductivity and the thermal expansion between silicon substrate and copper. With the devices become smaller and smaller, the reliability can be significantly affected by the CT mismatch between silicon and copper. The need for interposer materials with both high electrical conductivity and low CTE is being increased. Carbon nanotubes have attracted extensive attention due to its exceptional properties. It's promising low-dimensional material for many applications. The unique structural properties enable their superior applications as illustrated in this graph. In terms of neural probes, carbon nanotubes are kind of soft, like over 2 orders of magnitude softer than silicon, showing mechanical compatibility with the tissue. Carbon nanotubes also have very high surface area, good sensitivity. Using lithography, it can be made with high density. In terms of interposer, its low CTE and good conductivity make carbon nanotubes perfect candidate for via material. Plus, incorporated with copper, the composite is compatible with the interface of current copper materials. However, some studies using carbon nanotube as vias show that properties are still yet satisfied. Therefore, how to process the material into desired architecture represents an important step in utilizing their properties and applications. So, what is the challenge? For low aspect ratio, direct growth of carbon nanotube pillars is not difficult. The pillars can keep straight with good spatial resolution. However, as aspect ratio increases, direct growth of this freestanding carbon nanotube pillar, still maintaining the straightness becomes very challenging due to mechanical requirements. These are some published results. These are our preliminary results. Expanding makes these pillars difficult to use due to the loss of spatial resolution. To overcome this synthetic limitation, here is our approach. Our concept is very straightforward. Just like build a tall architecture, you need a support structure to make it stand straight. We first glue carbon nanotube pillars with the help of support so the pillars can keep straight. Then we remove the support to get the freestanding straight carbon nanotube pillars. Using the patented catalyst by lithography, carbon nanotube pillars were grown by chemical vapor deposition. With the help of support, we can grow highly straight, highly vertically well-ordered carbon nanotube pillar arrays. They're about 1.2 millimeter tall with 40 micron in diameter. Initial aspect ratio is about 30:1. Next, we need to remove the support. We use a combination process. First, a non-directional plasma etching to remove the top part of the support, followed by carbon infiltration to strengthen the pillars, then a directional plasma etching to completely remove the bottom part of the support. This combination process resulted in the most efficient, reproducible removal of carbon nanotube support. Here are the final freestanding carbon nanotube pillars. As you can see by these high-resolution SEM images, the CNT support was completely removed. This is the before as a wall structure we call the hedge, CNT hedge, and after that they are completely removed. But the pillars are still maintained their good alignment and straightness. This is another samples. So the final carbon nanotube pillars has a height about 1.2 millimeters, diameter about 20 micron. So the aspect ratio is 6:1. It's very high. So the spacing is about from 100 to 400 micron, depending on the samples. We can still get uniform spacing by keeping the straightness. Next, I would like to present two diverse applications utilizing this porous carbon nanotube structure. First is the CNT neural probe. Second is the carbon nanotube copper composite through silicon via interposer. Please refer to our published articles for the details. The first application is the neural probe. To begin with, we check the functionality of the carbon nanotube pillars as a neural probe. An individual probe was used to do this electrochemical response test using cyclic voltammetry. Here are the typical cyclic voltammetry curves of massive virology with its characteristic signature peaks, clearly shown. This result indicates the capability of carbon nanotube pillars to serve as electrochemical sensing probes. For neural sensing applications, we investigated the direct detection of doping using fast scan cyclic voltammetry. Here shows the current changes associated with the doping concentration, and here shows its signature peaks. This successful fast scan cyclic voltammetry demonstrated the capability of our carbon nanotube pillars being used as neural probes. To apply our carbon nanotube pillars to microelectrode array devices, it is necessary to evaluate the possibility of using microfabrication process to create the electrical connections that can individually address the probes. To do so, the carbon nanotube pillars were grown on patent tungsten lines, showing the process integration with conventional lithography and thin film processes. The second application is through silicon via interposer. Here is the fabrication procedure. We use a simple bottom-up assembly approach to fabricate the interposer. First, patent carbon nanotube pillars were synthesized and followed by a homogeneously high-content copper electrode deposition. Meanwhile, a through silicon via wafer was prepared by conventional deep RIE process with closely matched size of holes. Then, the CNT-CU pillars were inserted into the TSV substrate to form the interposer. Using a 3D manipulator, here is the final product. Please visit the invited talk from my colleague, Dr. Sundaram, for the details of copper electrode deposition. This is the final product. It's freestanding well-ordered vias. The vias were nicely filled, as can be seen in a close-up SEM image. The interposer was measured with high electrical conductivity, about half of the copper. In addition, We also measured its thermal expansion. Interestingly, the interposer shows a much lower CTE than copper, but very close to silicon. This close match of CTE can help improve the device lifetime by reducing the internal strain due to the CTE difference between the via material and silicon substrate. It is very important that the CNT assembly should possess a porous structure for copper deposition. Our supergross CNT forest can achieve a well-ordered, highly porous structure. Next, in order to maintain the shape of pillars and meet the vertical requirement for the later insertion process, a small amount of carbon coating was deposited to reinforce the forest structure. Then a two-step copper electrodeposition process was used to deposit the copper into the CNT forests. After the first copper step, well-distributed copper sheaths can be observed throughout the bulk of the pillars. Thanks to this uniform seeding, it provides a arrangement for uniform feeding of the remaining bulk and avoids the common problem of surface coating. This structural satisfaction enables the excellent properties of our CNT-CU TSV interposer. As compared with other reports, our interposer ranks among the best combinations of electrical conductivity and CTE. Here I show some more details about the structural changes. First is the carbon reinforcement. We deposit a small and controlled level of carbon coating to essentially glue the carbonative bundles junctions as a reinforcement. We examined the changes of the pillars after liquid process. As you can see, the pillar structure maintained very well with a suitable amount of carbon deposition. The next structural observation is after the first copper electrodeposition. Thanks to the highly porous CNT structure, well-distributed copper sheaths throughout the bulk of the pillars were achieved, as shown here. The copper sheaths uniformly and isolatedly deposited between the carbon tubes, clearly evidenced by this SEM image and EDX results. After the second copper electrodeposition, as a result of the homogeneous copper seeding, we can achieve a uniform copper filling of the bulk of the pillars. Here is an open cross-sectional surface with SEM and EDX, clearly showing the uniformly and adequately deposited copper inside the pillar. Next, I would like to demonstrate several applications using the CNT-CU TSV interposer. The first example, we used two stacked interposers as a junction for delivering power to an LED light display. Let me show you this video. This simple demonstration shows the basic functionality of electrical conduction in stacked chips in electronic devices. The second example highlights the high electrical conductivity and temperature tolerance by using the interposer as a power junction for an incandescent light bulb. The high power setting corresponding to a current density of about 4,000 ampere per square centimeter. And because of the high electric conductivity and small CTE mismatch, the power could be delivered without interruption or failure for over 200 days. This result demonstrates its high performance due to the high electrical conductivity and low CTE mismatch. The other demonstration was a flexible interposer, which could be used in flexible wearable electronic devices. Instead of using silicon as the substrate material, we used the PDMS. We embedded the cumulative copper pillars into PDMS monomer. After curing, the embedded pillars were released from the gross substrate, creating a freestanding flexible interposer. These pillars were 20 micron in diameter and 20 micron spaced. Well, this example does not make use of the low CTE, but it does demonstrate an ability to be applied to non-planar surfaces. Now, Let me summarize my talk. We developed an approach to overcome the synthetic limitations to fabricate challenging structures, very high aspect ratio 6:1 freestanding carbonated pillars. We demonstrated two diverse applications utilizing this porous carbonative structure. The CNT pillars are capable of acting as neural probes. Incorporated with copper electrode deposition, we demonstrate the feasibility of CNT-CO composite as a via material for TSV interposer, which showed copper level electrical conductivity and silicon level CTE, as well as significant decrease in CTE mismatch with silicon. Finally, I would like to thank our group members for their great support. Our colleagues thank the financial support listed here. At the end, thank you very much for your attention. Now I'm happy to answer your questions.
Okay, let's thank Professor Chen for this pre-recorded presentation with very exciting results. Since Professor Chen is not with us, if you have questions, you need to contact him directly, please. As we go on to our next presentation, which we will also see by pre-recorded video from Dr. Balasubramanian from BITS in Hyderabad, India, with the title Materials, Processes and Characterization of Rare Earth Doped Layered Ferroelectric Ceramics for Random Access Memory Devices. Please, can you start the video for us, Dr. Yingyan? Thank you.
Regards to everyone. My name is Lidia Matija and I'm professor at the University of Belgrade, Faculty of Mechanical Engineering, Department of Biomedical Engineering, and today I will present the work of my group. Now I will pass to presentation.
Sorry to interrupt. Is this the correct video? I think we are at a different one, materials, processes and characterization. The video before. Yes, number 6. Thank you.
Good morning, everyone. I'm Harihara Venkatraman, working as a faculty in physics department at BITS Pilani Hyderabad campus. Today, I'll be talking about the material processes and characterization of rare earth doped layered ferroelectric ceramics for its potential usage in non-volatile random access memory devices. The content of my talk are the following. To begin with, I'll be describing the importance of layered ferroelectric materials for its potential usage in non-volatile random access memory devices. Next comes the fabrication of layered ferroelectric ceramics such as strontium bismuth tantalate and barium bismuth neogate, followed by the structural and microstructural studies. And then I'll be talking about the dielectric and ferroelectric characteristics of these layered ferroelectric compounds. Finally, my talk will end with the conclusion part. So as we all know, there are two types of memory. The first one is volatile random access memory. The second one is the non-volatile random access memory. So what is the specialty of NVRAM over VRAM? It has superior performance. It has high speed read and write operation. It has low power consumption. The data can be retained for a long time even when the power is turned off. So one of the classical materials that was widely used for NVRAM device was lead zirconium titanate. I have shown here the unit cell of lead zirconium titanate in which the lead atoms are located at the corners of the unit cell. We have oxygen ions at the face center, and at the center either we can have zirconium or titanium. So whenever an external electric field is applied to this material, the central atom will be displaced either up or down, thereby creating the permanent polarization states. So there are a few drawbacks associated with this particular material. The first one is it undergoes severe polarization fatigue, means the material can withstand up to 10 power 6 to 10 power 8 read per write cycle, and also it is toxic. So what are the major challenges involved in developing NVRAM devices? The material should possess high fatigue resistance. The material should have high remnant polarization with low coercive field. And the material also should possess low leakage current, and it should be non-toxic. So these are the major challenges involved in developing NVRAM devices. So the renewed interest stems from the layered ferroelectric materials such as strontium bismuth tantalate and barium bismuth niobate, due to low fatigue with polarization switching, and also it is lead-free. There are a few drawbacks associated with these layered ferroelectric compounds. The first one is low remnant polarization. The second one is high processing temperature. So much effort has been made in the literature in order to improve the physical properties of layered ferroelectric compounds such as strontium bismuth tantalate and barium bismuth niobate. So I found in my research work the most effective approach to enhance the physical properties of these materials is by doping rare earth ion on the bismuth site in the crystal lattice of the layered ferroelectric materials. So what is the reason for choosing rare earth ion as a dopant? The first one is ionic size. The ionic radio of samarium ion is less than that of bismuth ion. The second one is it appreciably decreases the DC conductivity of these compounds. So in our research work, we have successfully replaced bismuth ion by samarium ion in strontium bismuth tantalate and barium bismuth niobate ceramics and studied for various physical properties. I have shown here the crystal structure of strontium bismuth tantalate, which belongs to the N equal to 2 member of the Arvillous family of ferroelectric oxides. Means it contains 2 perovskite-like TaO6 octahedral units stacked between the bismuth oxide layers, as shown in this slide, in which A sites are occupied by larger cation, that is Sr2 plus, and B sites are occupied with cations of higher valency, that is Ta5 plus. So these are some of the interesting features of this particular material. It crystallizes in non-central symmetric group. It is orthorhombic at room temperature, and it has interesting physical properties. I have also shown the crystal structure of barium bismuth niobate. So this compound also belongs to N equal to 2 member of the Arvillous family of ferroelectric oxides. Here it contains 2 perovskite-like NBO6 octahedral units stacked between the bismuth oxide layers, in which A sites are occupied by larger cation, that is Ba2 plus, and B sites are occupied with cations of higher valency, that is Nb5 plus. And these are some of the interesting features of this compound, that is barium bismuth niobate. It crystallizes in non-central symmetric group. It is orthorhombic at room temperature, and it has interesting physical properties. So I have fabricated samarium dope strontium bismuth tantalate and samarium dope barium bismuth niobate ceramics by using low temperature molten salt synthesis route, in which I have used KCl as a flux. So after preparing these compounds, we have subjected it for various physical property studies that include dielectric and ferroelectric characterization. So first, I'll be talking about the structural, microstructural, dielectric, and ferroelectric properties of samarium doped strontium bismuth tantalate ceramics. So in this slide, I have shown the X-ray diffraction patterns recorded for undoped as well as samarium doped strontium bismuth tantalate ceramics. So these X-ray diffraction patterns clearly reveal the presence of monophasic layered perovskite structure. So in this slide, I have shown the micrographs recorded for undoped as well as 5 mole % samarium doped strontium bismuth tantalate ceramics. So these micrographs clearly reveal the presence of plate-shaped grains, and the average grain size of these ceramics are found to be in the range of 1 to 2 micrometer. And we have also carried out the dielectric property measurement as a function of temperature for undoped as well as samarium doped strontium bismuth tantalate ceramics. So it is observed that the Curie transition temperature shifts towards lower temperatures with increase in samarium content, and also the magnitude of the peak dielectric constant decreased with increase in samarium concentration. So this could be attributed due to the reduction in the distortion of TaO6 octahedron of strontium bismuth tantalate ceramics. So I have provided the values of the Curie transition temperature as well as dielectric maximum in this present slide for your kind reference. This is an important observation. The tunability of the Curie transition temperature towards lower temperatures with samarium doping will have a significant influence on the remnant polarization in strontium bismuth tantalate ceramics. So in this slide, I have shown the variation of polarization versus electric field for undoped as well as 5 mole % samarium doped ceramics. It is interesting to note that the remnant polarization value increases with increase in samarium concentration. And this might be due to the increase in the structural distortion of perovskite unit in the crystal structure of strontium bismuth tantalate ceramics. So in the second part, I'll be talking about the structural, microstructural, and dielectric properties of samarium doped barium bismuth niobate ceramics. So I have shown here the X-ray diffraction patterns recorded for the different compositions of samarium. So in all these X-ray diffraction patterns, a monophasic layered perovskite structure is retained. And we have also recorded the micrographs for undoped as well as samarium doped barium bismuth niobate ceramics. All these micrographs clearly reveal the presence of well-packed plate-shaped grains. And this plate-shaped morphology arises due to the anisotropic nature of the crystal structure. We have also carried out the dielectric constant measurement as a function of temperature for different concentrations of samarium. It is found that the dielectric maximum shift towards the lower temperatures continuously with increase in samarium concentration. And also the magnitude of the dielectric maximum decreased with increase in samarium doping. And this could be attributed due to the decrease in the distortion of NBO6 octahedron of BBN ceramics. So in this slide, I have provided the value of Tm as well as dielectric maximum for different compositions for your kind reference. So the tunability of TM towards lower temperatures with increase in samarium concentration clearly reveal that it will have a greater influence on the ferroelectric properties. So these are the conclusions. The X-ray diffraction patterns confirm the monophasic layered perovskite structure of strontium bismuth tantalate as well as barium bismuth neobate ceramics. The scanning electron micrograph revealed the presence of well-packed plate-shaped morphology. So in general, samarium doping affects the physical properties of strontium bismuth tantalate and barium bismuth neobate ceramics. And we have used the following characterization techniques for structural analysis, for microstructural analysis, for dielectric studies, as well as for ferroelectric studies, for our proposed compounds. Thank you all. I also take this opportunity to convey my sincere thanks to the organizing committee for giving me an opportunity to present our recent research work at this extreme conference. Thank you.
Yes, let's thank Dr. Balasubramanian again for this very interesting presentation. Also here, the speaker is not present for questions, so we have to move on. I'm happy that our next presenter is with us. So let's welcome Professor Matija from the University of Belgrade for the presentation Investigation of PMMA carbon-60 nanocomposites as nanophotonic materials for potential medical application. So, Professor Matija, you want to give the presentation live?
No, I don't want to say it live. So just put the recorded presentation, and I will stay to answer the possible question.
Yes, sure. And let's do it like that.
Thank you. Regards to everyone. My name is Lidia Matija, and I'm professor at the University of Belgrade, Faculty of Mechanical Engineering, Department of Biomedical Engineering, and today I will present the work of my group. Now I will pass to presentation. The title of our work is Investigation of Polymethymetacryl C60 nanocomposite as nanophotonic materials for potential medical application. Beside me in this investigation participated Dr. Ivana Stankovic, Milinčić Milica, and Professor Đuro Koruk. Here I will present you our motivation, what materials and methods we used, results, discussion, and conclusions. Motivation was that actually nowadays we are faced with the increasing use of electronic devices and indoor work, mostly under artificial lighting. This was especially the case during the pandemic, where the majority of the world's population worked online. It is well known that high energy light, like UV blue light, can damage eye structure. In fact, too much exposure to ultraviolet light from sun increases the risk of eye diseases, including cataracts, growth on the eye, and cancer. On the other hand, our knowledge about the effects of the blue light are still being researched, but it is known that it affects the circadian rhythm. In particular, the excessive blue light is theoretically harmful, yet an adequate blue light is necessary for normal visual function. The question arose, can we protect our eyes and how? Material that we use is polymethymetacrylate or PMMA because it's proved to be one of the most convenient high molecular compound widely used as matrices for fullerene containing nanocomposites, and also because of its availability, low cost, lightness, and other characteristics. The second and the most important one is molecule C60 because of its unique property that we all know, like icosahedral symmetry, 12 pentagons, 20 hexagons, and the size of C60 with p electrons cloud is about 1 nanometer. In order to apply our scientific knowledge and encouraged by the literature data like development of optical limiters for eye protection in the form of spectacles that exhibits reverse saturable absorption and optical limiting for polymer nanocomposites consist of C60 in PMMA, we synthesized nanocomposites with different concentration of C60 molecules, 0.025 weight, 0.05 weight, 0.075 weight, and 0.1. The method that we use is proposed by Cavucci and all, and this reference is at the bottom of the slide. The main goal was to investigate which concentration is the most convenient for the eyes and to protect eye damage. Further, we used spectrometers, UV spectrometer, actually 3 of them, Hamamatsu, then International Light Technologies USA, and Perkin Elmer Lambda 950. Then magnetic force microscopy produced in Gel, Japan, GSPM-5200, scanning probe microscopy, then halogen bulb, Osram 41900 SP Germany, and linearly polarized light that the light source was the Bioptron device produced in Scepter International Company with the same halogen bulb and Brewster mirrors which transform diffuse light into the linearly polarized one. Magnetic force microscopy was used to demonstrate the influence of different concentration of fullerene molecules in PMMA on the attraction and the repulsion forces and consequently on the complex structural and optical properties. It is demonstrated, as one can see at the figure, that the structure of the complex directly correlates to the ratio of unpaired and paired electrons within the material. Based on investigation, it is demonstrated that PMMA C60 nanocomposite having 0.025 weight concentration of C60 has the best structural and optical properties to be applied as a new material for spectacles. This figure is presented UV spectrometer of different filters that we produced. And since the difference of the specific energy, illuminescence, temperature, and chromaticity of the sun plus PMMA and PMMA plus C60 with different concentration of C60 is significant, as one can see, the best solution has PMMA plus 0.025 weight C60 complex. This complex can be used for both indoor LED halogen neon lights and outdoor lenses for glasses, while other 3 types of complexes may be used only for outdoor use. Based on these results, optimal concentration of C60 for only indoor use is about 0.025 weight. It is well known that blue light might be harmful to the retina. Nanomaterial forensic C60 and PMMA transform diffuse light into harmonized light and absorb violet, blue, and UV wavelength. In this investigation, is presented that the use of blue blocking filters with fullerene with the concentration I mentioned can significantly decrease the high energy blue part of the spectrum present in natural and artificial light sources, and at the same time increase the overall comfort of daily tasks while and after using them. What is actually the main trick, let's say? During the light C60 interaction, orientation of C60 molecule in space and time is very important. Light travels with the speed of about 3 multiple 10 to 8 meters per second, while the C60 molecules has a rotational diffusion constant in the solid state about 1.8 multiple 10 to 10 per second. At 283 Kelvin, the molecular reorientation correlation time is 9.1 picosecond. It would not be the same situation where photons interact with pentagons or hexagons. So what is the main trick? The trick is that from energy point of view, hexagons in molecule 60 is breathing, and photons pass through hexagon and penetrate inside cage and interact with 0D cavity, which we named 0D quantum cavity. This result was confirmed by Stuttgart research group from Max Planck Institute that demonstrated electrically driven single photon emission from localized structure, as one can see at this figure, defects in C60 STM experiment, and revealed electroluminescence optical spectrum in the range from 600 to 900 nanometers with a dominant peak at 728 nanometers, which is overlapping with our results that was performed using UV spectrometers. So during light C60 interaction, photons in cavity cage generate excitons. Since the exciton creation and annihilation are key processes relying on charge exciton photon conversion, the upper and lower polaritrons are generated as a quantum fluid of light. This is confirmed in our experiment also using UV spectroscopy, where we recorded spectra of white lead diode and spectra of white lead diode, which is passing through our blue blocking filter. As one can see at this slide, blue blocking filter might offer an effective protection from ocular pathologies while providing a better comfort in daily activities. So what was the challenge? Why we use polarized light? Because it is natural reflection when we are surrounded by snow or when we are at the seaside and we are under influence of reflection of the sea. It will be very interesting to know, is there difference of influence of diffuse and linearly polarized light of green and red light before and after the interaction with C60 polymetamethacrylate nanocomposite. So in diffuse light, electrical and magnetic planes, which are always perpendicular, of photons are randomly oriented, as one can see at the figure. Linear polarized light, electrical and magnetic planes of photons are oriented in planes according energy values blue, green, yellow, and red. Difference between the intensity of diffuse light and linearly polarized light before interaction with C60 in the range from 200 to 1100 nanometers is presented on diagram above, while after the interaction with C60 is presented on figure below. In total, differences without and with C60 are in UV-Vis near domain between 200 and 1100 nanometers, 42.26%. To explain the differences of areas under curves, specific density of energy between diffuse and linearly polarized light before and after interaction with C60 molecules, the physical property of C60 should be considered as well as the planes of the electrical field and magnetic fields of photons. These fields are perpendicular to each other and have the same frequency but different amplitudes. When visible light interacts with valence electron of the matter, the effects of the electrical field are dominated by those of magnetic fields, and the difference may be 4 orders of magnitude. Despite that, magnetic forces is weaker than electrical forces. It is used in electrical motors and many other devices because usually the net electric force between two bodies is 0. However, when charges are moving in two bodies, the magnetic forces are not 0. It is caused by C60 molecule with a diameter about 1 nanometer, which is a dynamically entity with a rotational diffusion constant approximately 10 to 10 per second. The 60 p electrons on the surface of C60 are moving very fast and generate a magnetic field that strongly interacts with the magnetic field of the photons. It means that orientation and order of planes of the magnetic field of incoming photons are very important for light interaction with C60. Another C60 property, wave-particle duality, is important for its interaction with light. Here is schematically presented how light behaves when passing through C60. The hyperpolarizability property of C60 and photon Hall quantization of its optical angular moment create a new type of illumination that we call sunflower shape, as one can see at this figure. We did several biomedical studies and we get approval, ethical approval, and we did it with our colleague from medical school from University of Belgrade. Blue blocking filters with fullerene C60 increase the overall comfort of daily tasks while and after using them. The initial ophthalmology study based on 50 volunteers indicate that spectacles with EPMM-INV-3 with fullerene concentration of 0.025 weight have advantages in contrast sensitivity compared to the existing similar spectacles in use. The study showed that subjectively, the spectacles with lower concentration of fullerene was statistically significantly superior in all different daily activities for near vision, for mid-distance vision, and for distance vision. The next study was the initial pilot study with participation of 28 volunteers showed that nanophotonic glasses had a statistically significant effect on the quality of the life related to vision 3 months after use in the entire study sample. The data and the more details can be found in the reference that is below at the bottom of this slide. The next slide was the result of study that involved 80 clinically healthy volunteer participants has shown that the effects of light passing through a fullerene filter on the visual analyzer and the structure of the central nervous system has a positive effect on the mental performance of a person by increasing the efficiency of information processing by visual analyzer and creating better conditions for motor response. Also, in additional study with 17 volunteers, a significant decrease in the activity of frontal and central zones of the right hemisphere in the delta and beta 2 ranges was detected. A significant increase was evidenced in the activity of posterior cingulate cortex in the theta and alpha ranges. This indicates improved coordination of visual information, attention, assessment of the position of the body, inhibition of irrelevant information, and optimization of decision-making processes by using fullerene filter. The more detail can be found at the reference at the bottom of the slide. So in the conclusion, we can say that in this investigation is presented the use of blue blocking filters with fullerene C60 nanophotonic spectacles with 0.025 weight percentage of C60 can significantly decrease the high energy blue part of the spectrum present in natural and artificial light sources. It is experimentally shown that during light C60 molecule interaction, exciton is created and with photons generate polytron. It is demonstrated that the total difference of 42.26% between diffuse and linearly polarized light of the same source of light before and after the interaction with nanocomposite complex exists. Polaritron light of C60 generate a coupling of photons and exciton beneficial action on physiological function of brain such as depression and anxiety. These filters might be an effective mechanism to protect eyes from ocular pathology, alleviating the functional loss of retinal photosensitive cell in the expected exposure to the blue-rich light in the living ambient is high and long enough. For final conclusions of ophthalmological benefits as well as brain visual information processing, further investigation is needed. Thank you for your attention and have a nice day.
Thank you very much for this fascinating presentation. I think we have time for one question. I don't see a question in the chat. Is someone
Okay,
around?
so here are the spectacles, so I'm wearing it.
Okay, that's very nice to see.
Yes.
Maybe I ask one thing. Can you comment on the long-term stability of your materials? I mean, if they are used for spectacles and they're exposed to light for hopefully years, will they withstand that, or is there some
Up to
bleaching
now,
effect or things?
okay, based on current investigation, yes, they are very stable. Unfortunately, we have one accident that our main doctor that guided this ophthalmological study died due to corona, and we are now searching for another medical doctor to continue with this depression and this psychological feelings by wearing glasses. And also we got approval that we can even use them for kids. To protect their vision because they are very often at Android cell phones, computer, etc. So the recommendation at the beginning is that to be weared 2 to 3 hours per day for 2 or 3 weeks, and then the eye gets used to these spectacles and can be used for more hours.
Okay, thank you very much. That's really fascinating.
Thank you. Bye-bye.
So let's continue now to the final presentation for today. And we have Professor Zhang with us from the University of North Carolina at Charlotte from the USA, who will present to us electron-phonon coupling and semiconductor nanostructures, intrinsic and extrinsic tunability demonstrated with zinc tellurium nanowires. Looking forward to hearing your presentation.
Thank you for the introduction. Actually, I thought this is required to submit a recorded video, so I already submitted one. We might as well just use that one. I will be here also answer question.
Yes, sure. So we can watch the video and then afterwards come back for questions.
First, I would like to thank the conference organizers for inviting me to give this talk. The title of talk is Electron-Phonon Coupling in Semiconductor Nanostructures, Intrinsic and Extrinsic Tunability Demonstrated with Zinc telluride Nanowires. I'm Yong Zhang from University of North Carolina at Charlotte. Here's the outline of my talk. First, I'm going to give a brief introduction to the electron-phonon coupling. Then the framework to treat electron-phonon coupling. There are two distinctly different approaches. Then how we probe electron-phonon coupling using resonant Raman scatterings. Again, there are two theories to explain the result. And then I will show the experimental data from using resonant Raman scattering to study bulk and nanostructures, then the conclusions. And for 30 years, people have been asking this question: is electron-phonon coupling weakened in semiconductor nanostructures? There is a considerable amount of controversy. And why this is important? Of course, this is fundamentally important science issues, but also there are a number of practical implications. And in the early days, people have suggested there's something called phonon bottleneck effect when you go in from a bulk to a nanostructures. So this phonon bottleneck effect is related to electron-phonon coupling, and they are important for a number of things: hot carrier devices, multi-isotope generations. So how we deal with electron-phonon coupling in a semiconductor? If we don't consider electron-phonon couplings, we can simply write the wave function for the total system as a product of electronic part and the phonon part. And they can be independently solved from two Schrodinger equations. Now with coupling and these electron-phonon coupling terms, and these two equations become coupled, then the wave function of electronic part actually depends on the atomic position. So obviously it's going to be very difficult to solve them exactly. So people have taking two general approaches. In one case, we only consider the electron-phonon coupling in the electronic states, but not in the phonon states. So in this case, in the perturbation, the first order perturbation would be 0 for the bulk states. Then all the effects comes from second order or higher order perturbation. Most known effect is so-called indirect band gap transition, and something like this. So this is a result of second order perturbation. And higher order perturbations, you can get Raman scattering and also large polynomial effect. And the other extreme to deal with the coupling is to consider only the electron-phonon coupling in the phonon states. If we take a linear coupling approximation, then we calculated this matrix element. So I already mentioned for the bulk states, this is going to be 0. However, if these electronic states are localized states, then they can be non-zero. And because of this, the atomic configurations will be different between, say, initial state and final states. Then their phonon states are not orthogonal to each other. So this effect causes a shift in the electronic state. And also, the electron-phonon coupling strengths can be measured by a so-called Huang-race factor, which can be calculated from this matrix element. Now, how do we probe electron-phonon coupling in semiconductor nanostructures? And they cannot be measured directly, so we use different optical techniques. Most widely used techniques is resonant Raman scattering. So this is one example. When you do resonant Raman scattering, say on zinc telluride, and you will see many phonon replicas. But interestingly, you see the first order one is almost 0. And now for many nanostructures, and people have done similar measurement. The questions are the result of really genuine size-dependent effect, or could be due to something else. For instance, the defects included in the growth during the growth, and also perhaps you just use too much lasers that induce defects. Then, which electron-phonon coupling mechanism is appropriate? One theory is to use lattice relaxation, and this is most widely used in the nano community. In this theory, a reduced R-to-1 ratio, meaning the ratio between the two phonon and one phonon, imply a weakened electron-phonon coupling. And the other theory, using astonic states as intermediate state for the Raman scattering. For this theory has mostly ignored in the community. However, this theory will imply that the reduced R-to-1 ratios, meaning the enhance of the first order Raman scattering, actually is enhanced in electron-phonon coupling. So specifically, these are the two theories. And one is based on phonon intermediate states, and that was developed by Black in 1961, and used this formula to calculate the Raman scattering cross-section. And these are the matrix elements, which is supposed to be non-zero due to the lattice relaxation. And the second one is based on astonic invariant states. And again, this is very complicated theory. And none of these approach can be easily calculated. However, I can say there are some major issues with the theory involving the phonon intermediate states. One is for the bulk state, there will be no lattice relaxation because this matrix element will be 0. So obviously, the Black theory does not apply to the bulk. Also, this theory cannot explain the forbidden 1LO transition and also those ratios between different orders. And if resonant normal scattering has already been observed in the bulk crystal, then the phonon-based mechanisms, even if it's applicable, it might not be adequate for the nanostructures. So specifically, how people do use the theory for the nanostructure. And first, we have to assume these matrix elements are non-zero. If they are non-zero, you can calculate it, the R21, the ratio between second order and first order will be non-zero. Then you can derive, from that you can get a Horn-Race factor. However, it's inconvenient to use experimental data as a bulk reference because for the bulk spectrum, this ratio actually is infinity. That would imply that you have infinity size Horn-Race factor. So instead, people are actually using a different theory to calculate the reference value. And this was a theory developed for something else, but has been widely used for this community, which can calculate a Horn-Race factor, for instance, for most two-slit semiconductors in the order of 2 or 3. As I said, this has been a 30 years process. And one of the most earliest work was reported in 1989, where it was shown this 1 LO intensity is much enhanced compared to the bulk structure in this quantum dot. So the conclusion is the electron phonon coupling has been weakened in nanostructures, in this case, quantum dots. However, over the years, many people have reported many conflicting results, either reduce or increase, or sometimes there is no change. And to say if there's a change or not, we first need to have a reliable bulk values. So according to this early work at low temperature, and basically this R-to-1 ratio is infinity. Now for room temperature, we actually measure many bulk materials. What we found for high quality bulk materials, the ratio is still very big, in order 8 to 10. So as we show here for many bulk zinc telluride samples, if we measure a set of thin film samples, even they are somewhat defective, and you still get very large values. However, if we put in lots of defects to the bulk material, you can see this value is going to reduce. And if for highly defective thin film, it can go even below 1. So this tells us even just a defect, you can get a very large range of tuning. And if you use a Bragg theory, you will imply you have a very large electron phonon coupling in the bulk materials. Now, here's the spectrum for the defective samples and compared to a non-defective or very high quality zinc telluride. And now let's look at the data for zinc telluride nanowires. And there has been some reports in the zinc telluride nanowires, and particularly this one. It shows very nice dependence of R-to-1 ratio as a function of nanowire size, and with a reference value calculated using that theory I mentioned. And that looks very nice because what people want to see, the electron phonon coupling reduce with reducing size. And we have studied a large number of nanowires with size down to about 30 nanometer up to even close to 1 micrometer. What we found is there is very little change for the electron phonon coupling or the R-to-1 ratio. So here is the bulk, and here is a 84 nanometer nanowires. So the change is very small in terms of ratio. Now, if we put all the data together, and first, if we use a reliable bulk value, it's much greater than what has been reported. Now, adding all the measured values from our nanowires, you see, even with some fluctuations in general, these values are much greater than what have previously reported. Also, there's very little change from almost microscopic size to nano scale size. So we know the impurity and defects can induce change. And there's another way to induce change, which is to use a laser. And here is a very large nanowires. If we use different lasers, we can see with higher laser power, you started to see a somewhat enhanced 1LO. Also, you started to see a defective peak related to tellurium. And for a smaller nanowires, you can see a more drastic effect change due to the laser illumination because that induces defects. But with this observation, we actually can have a way to control these ratios. And here it shows in different samples, either high quality bulk materials or thin film, and you can illuminate it with lasers, or just by introducing defects, you can get almost any values you want with some accuracy. And here's a conclusion of my talk. The first is, I want to say the resin Raman scattering cannot be used to extract one race factor. And there's no lattice reduction in the bulk material, and there's minimum even in the moderately sized nanostructure. Let's say for the nanowire case, maybe down to 30 nanometers. And the reduction in this 2LO to 1LO ratio implies increase rather than decrease in electron coupling. And we have a very large intrinsic 2LO to 1LO ratio and no significant change down to 13 nanometers. However, extrinsic effect can greatly modify the NLO ratios. They can be either due to impurity or defects incorporated during the growth, or laser-induced defects during the measurement. So because of this result from the gene terror nanowires, we believe many other nanostructures should be re-examined carefully, and we need to develop a proper theory for this. And there are some practical applications, and it can be used for some memory devices, and we can actually have programmable nanoscale barcodes. And finally, I would like to acknowledge the support and collaborators. Thank you for your attention.
Thank you very much, Professor Sang, for this very exciting and interesting presentation.
Thank you.
There's time for questions now. Please use the chat or even ask directly. Maybe I can start with a question. From what you have investigated or from what you can imagine here, do you think this effect is specific for zinc telluride, or would you expect it to be similar corrections also valid for other nanowires, other nanostructure materials?
I think the phenomenon should be quite general. We know many of those nanostructures were made with defects, like you have different kind of nano dots embedded in some structures. We really don't know the status of defects or impurities. And also, many people are just putting too much laser when they did the measurements. In particular, I know you probably have experience. You want to study individual nanowires, and the signal is so weak, you just put in more power until you get comfortable signal, then you already change it.
Yes, maybe a follow-up question. Are there, in literature or what you experience, differences in these ratios if you measure ensembles, if you measure individual nanostructures?
Use a different measurement like absorbance and
Raman. I mean, if you take maybe the same technique, but if you investigate, because you mentioned before, if you want to investigate single nanostructures, then it's getting more challenging. Is that reflected in the values, so that if your studies on single structures report other values than studies on ensembles of nanostructures, or?
I think each technique probe something differently. It's hard to make a meaningful comparison. For instance, resonant Raman, the underlying mechanism is very different from absorption of photoluminescence. So you can always take the ratio of the two, and that doesn't really make too much sense. Like even in the bulk materials like gallium nitride, people would derive Hwan race factor, but that actually, in my opinion, that has nothing to do with Hwan race factor. It just you can get a ratio of the 1 phonon, 2 phonon.
Yes. Thank you. Okay, if there are no further questions, then let's thank Professor Zhang and also all the speakers of this session once more for these very exciting input and presentations that we got here. And with that, I close the session, and yes, there's a half-hour gap now until the next sessions continue at 1 p.m. Pacific time. Thank you very much.
Thank you, Chair. Bye-bye.
Thank you for your host, and our section will begin at 1 o'clock later.
And a special thank you also for the support from you for showing videos and everything, for your strong local support here. Thank you.
See you later.
Hello, everyone. Now we have the lunch break. And after 30 minutes, we will be back with a new session. That is functional composite materials. So have a good lunch.